Hello and welcome to Sleepy Science. I'm really glad you're here. Maybe your day was long and full. Maybe your mind feels a little crowded. Or maybe you just enjoy letting your thoughts float in the quiet company of cosmic wonder. Tonight we won't rush. We'll drift slowly and gently through one of the deepest questions anyone can ask. Where is the center of the universe? As it turns out, that question opens the door to many more. What if there is no center at all? What if galaxies aren't flying away, but space itself is growing between them? What if we can only see a small part of the universe, not because it ends, but because light hasn't had time to reach us yet? What if space is not a thing, but a process? As you listen, we'll explore how everything around you might be stretching in ways you cannot feel, how your position in the cosmos has no fixed meaning, and how the entire universe could be infinite while still keeping secrets beyond your reach. You don't need to understand everything. You don't need to follow every concept. Just allow your thoughts to soften. Let go of the need to know and invite in the joy of wondering. Whether you're listening under a warm blanket, gazing out at a quiet sky, or just letting your body rest beside a soft lamp, this space is yours. If these calm explorations make you feel more peaceful or more awake to the beauty of the unknown, I'd love for you to like this video and subscribe. It helps more thoughtful minds find their way here. Now take a deep breath in. And as you slowly breathe out, come with me into a quiet journey where space is not what it seems. Time flows at different speeds, and the edges of what we can see are not the edges of what is real. Every point in space sees itself as the center. You might think the center of the universe is a place, some glowing dot of origin you could point to, if only you had the right map. But what if the universe doesn't have a center at all, and instead, something much stranger is true? Every point in space, including where you are sitting right now, experiences itself as the center of cosmic expansion, but because space itself expands evenly in every direction from every location at once. And the more you think about that, the more it starts to challenge your everyday assumptions about up, down, here, and there. Because in a universe like ours, one with no edges and no center, the rules that guide your sense of position don't just bend, they dissolve. And what's left is a reality far more beautiful, far more equal, and far more humbling than the one you first imagined when you looked up at the stars. It all begins with a strange observation in astronomy. Wherever we look in the sky, distant galaxies are moving away from us, and the farther they are, the faster they appear to be receding, almost as if we're sitting on a cosmic throne and everything is running away from us. But if an alien on a galaxy 10 billion light years away did the same measurement, they would see the exact same thing, as if they too were at the center of everything. And so would a third observer on a galaxy halfway between us. This isn't an illusion, and it's not a trick of light. It's a deep truth about the way the fabric of space behaves, and it forces us to let go of the idea that the universe is like a balloon with a dot in the middle where it all began, because what it's really like is more subtle and elegant. It's like being on the surface of that balloon, a two-dimensional skin stretched in all directions, where every point sees every other point getting farther away, not because they're all moving through space, but because space itself is expanding, stretching like a flexible grid. And when you live on the surface of that grid, no matter where you stand, the stretching looks the same in every direction, so your position feels central even though it's not. And this leads to one of the most mind-bending ideas in modern cosmology. The universe doesn't have a center the way a room or a circle does, because it isn't expanding into something. It's creating more space from within itself, and because that creation happens everywhere equally. Every observer feels like they're in the middle of the action, like bubbles expanding on the surface of a rising loaf of bread, none more central than the others. And that's why, even though we often say the universe started with the Big Bang, it's not correct to imagine it as an explosion from a single spot in pre-existing space, because the Big Bang happened everywhere at once. Not in one location, but in all of them simultaneously. And what was born in that moment wasn't matter flying outward, it was space itself beginning to stretch and time unfolding alongside it, so that any point you could imagine, whether it's the surface of Earth or the heart of a distant galaxy, can trace its history back to that same moment, not from the outside looking in, but from the inside growing out. And here's the part that may surprise you most. Even though the galaxies appear to be racing away from us, they're not moving through space the way cars travel on a road. They're mostly stationary, and it's the road itself that's getting longer between them. So when we say the universe is expanding, we're really saying that the distances between things are growing, because the fabric beneath them is stretching, like dots on an inflating balloon. And that's why everyone, everywhere, sees the same expansion from their own point of view. It's not a matter of motion, but of geometry. And that's why every point in the universe sees itself as the center. Now, you might ask, if everything is expanding away from us, shouldn't we be able to look in one direction and find the spot it all began, like finding the splash at the center of a ripple? But the truth is, there is no such spot, because space didn't explode into a bigger room. It stretched itself into being, and it keeps stretching, so that wherever you are, the sky looks more or less the same in all directions. And that symmetry, that smoothness, is what convinces scientists that we're not in a privileged location. We're just one point among countless others, each with the same right to claim the title of center. Not because we're each the origin, but because there is no single origin anymore, only a shared unfolding of space and time that began everywhere together. This isn't a trick of perspective, and it's not a poetic metaphor. It's a measurable fact, confirmed by decades of observations. The redshift of distant galaxies, the distribution of cosmic background radiation, and the uniformity of cosmic expansion all tell the same story, one that removes us from the throne, but gives us something better in return. A universe where no one is truly off center, because center itself has become a perspective, not a position. And once you internalize this, once you let go of the idea that there's a fixed middle somewhere out there, you begin to see the universe not as a set of places, but as a pattern, an expanding structure where every point is stitched into the same unfolding, where there's no top, no bottom, no edge, and no privileged seat. Only the quiet miracle that space exists at all, and that you're part of it, not floating in it, but woven into it, carried by it as it grows in all directions at once. And perhaps that's the deeper lesson, that you don't need to be at the center to matter. Because in a universe where center is everywhere, meaning is not something granted by position, but created by awareness, by understanding, by the ability to wonder what it all means. So the next time you look up at the stars and feel small, remember, your location is not less than central. It is equally central, equally real, equally a part of this expanding story. And in that sense, you are not insignificant at all. You are exactly where you need to be, because everywhere is the center, and the center is everywhere. Why the Big Bang didn't happen in one spot. When people first hear about the Big Bang, they often picture a massive explosion in space, like fireworks going off from a single glowing dot, flinging stars and galaxies outward into the empty blackness. But this image, while dramatic, is deeply misleading, because the Big Bang didn't happen in one spot in space. It happened everywhere at once. And the reason that sounds confusing is because our brains are used to thinking of explosions as things that burst inside space, not things that create space itself. Yet that's exactly what the Big Bang did. Not filling a room, but building the room. Not a blast in the sky, but the birth of the sky itself. And once you grasp that, the whole structure of the cosmos begins to look different. Not like a cloud expanding from a center, but like a vast, unfolding fabric that grows equally from every point, including the one under your feet. This all starts with one crucial shift in understanding. Space is not a container that held the Big Bang. Space is a product of the Big Bang, meaning there was no places where it began, because place itself hadn't formed yet. No up, no down, no left or right. Only a hot, dense, formless state that didn't erupt into an existing universe, but became the universe in its earliest form. And it's not just theory, it's supported by real evidence. Cosmic microwave background radiation, the redshift of distant galaxies, the uniformity of temperature across vast distances. all of which tell a story not of stuff moving into space, but of space itself stretching, growing, unfolding like the surface of a rising dough where every part expands with every other part. So no matter where you are, the past leads back to the same event, not from the outside in, but from the inside out. And to make this clearer, scientists often use a helpful analogy. Imagine a balloon with tiny dots drawn all over it. And as the balloon inflates, the dots all move away from each other, not because they're crawling across the surface, but because the surface itself is expanding. Now translate that idea into 3 dimensions, and you begin to see what cosmologists mean when they say the Big Bang didn't happen in a spot. It happened in a state, and that state had no edges, no center, no background to erupt into, just a smooth, hot, dense condition that began to cool and spread everywhere at once. And when we say everywhere, we mean it literally, because every region of space, even the one you're in now, was once part of that beginning, not in the distance, but right here, right where you are sitting. Because in the earliest moments of the universe, there was no here and there to speak of. Just a tiny, dense, uniform sea of energy and potential, destined to become stars, planets, people, and thoughts. Now, this might lead you to wonder, if the Big Bang didn't happen at a single point, then how did it know where to expand, where to go? But that question itself comes from the wrong perspective, because it assumes space is a stage and the Big Bang is a performer, when really, the Big Bang is the stage itself being built moment by moment, and the expansion doesn't move into anything. It simply redefines what space is, how big it is, and what can fit within it. And here's where it gets even stranger. If you could somehow rewind the universe, compressing galaxies, stars, atoms, and particles closer and closer together, you'd eventually reach a moment where everything was squeezed into a state of such extreme density and temperature that all the familiar rules of physics start to break down. And this moment, around 13.8 billion years ago, is what we call the Big Bang. Not a pinpoint in space, but the beginning of space, time itself, the 0 point on the clock, the start of measurement, the birth of before and after. And that's why there's no way to travel back and see the Big Bang from the outside, because there is no outside, no place to stand apart and observe it, since even the dimensions needed for standing and observing were born within it. Now, this may sound philosophical, but it's grounded in real math and observation. General relativity predicts that space can curve and evolve, and the solutions to Einstein's equations describe a universe that isn't sitting inside a larger room. It is the room, and that room is dynamic, able to swell and shift and grow without needing extra space to grow into. So asking, where did the Big Bang happen, is like asking, where on earth did the Earth begin? It didn't begin in a point on its own surface. It's the surface that began, and everything else, including that surface, came from within the same moment of birth. And to understand how we know this, you only have to look at the sky. Everywhere you look, galaxies are moving away from you, and the farther away they are, the faster they're retreating, which would suggest, if you didn't know better, that you're at the center of everything. But as we've already seen, everyone in the universe observes this same pattern, meaning there is no single origin point in space, just a shared history of expansion from every direction. A uniform swelling of distances, not motion through emptiness, but the growth of the emptiness itself. And if that sounds unsettling, it's because we're not used to thinking of nothing as something that can grow. But in cosmology, even emptiness has shape, structure, and a role to play. And the Big Bang is not just the moment when everything got hot and fast. It's the moment when space, time, and laws themselves began to apply. And that's why it didn't begin in a corner, didn't burst from a speck, didn't leave debris in one direction, but instead left an echo in all directions equally. An imprint still visible today in the cosmic microwave background, which is the leftover glow from that early fire, now cooled to just a few degrees above absolute zero, but still surrounding us in every direction, like the afterglow of a light that shined not from a single point, but from all points at once. And when we say that, we're not being poetic. We're describing what astronomers have measured, with satellites like Cosmic Background Explorer, Wilkinson Microwave, Anisotropy Probe, and Planck all confirming that the early universe was astonishingly smooth, with tiny fluctuation, but no signs of a central blast. No pattern that points to a favored direction or location. Just a vast, even field of beginnings, unfolding into stars and dust and eventually life. All from a place that had no place. A moment that created all other moments. And that's why the Big Bang, despite its name, is not an explosion in space, but an expansion of space, not a fiery burst from one place, but a universal blooming of being. And when you finally understand that, the story of the universe becomes even more wondrous. Not just because it's vast, but because it's shared, because every atom in your body once came from that everywhere. From a time and state that didn't need direction, only unfolding, and even now, you are still riding the wave of that first expansion, carried through a cosmos that continues to grow, not away from a place, but into itself, and into the future. You're not at the center, but you're not off-center either. It's easy to feel small when you stare up at the night sky. Easy to believe you're drifting through space on a forgotten little planet tucked into a corner of the universe that no one remembers. But what if I told you something quietly profound? That while you are definitely not at the center of the universe, you are also not off-center either, because in a universe like ours, where space itself is expanding in every direction, from every location, there is no special middle, no privileged seat, no throne at the heart of it all, which means there's also no outer edge, no forgotten balcony where your life unfolds unnoticed. And once you realize that, your sense of place doesn't disappear. It transforms. This idea begins with a simple truth from cosmology. When we observe the most distant galaxies, we find that they are all moving away from us. And not just drifting, but accelerating, as if space itself is stretching between everything like taffy, and the farther away an object is, the faster it recedes, which would make it easy to think we must be sitting at the center of this cosmic blooming. But here's the twist, and it's one that changes everything. Observers in those distant galaxies would see exactly the same thing from their point of view, with every other galaxy appearing to fly away from them too. And the same goes for someone halfway between, or in any other galaxy across the visible sky. What this means is that there is no central hub where it all began, and everything else spread out from no lighthouse in the darkness, from which the cosmos unfolded, because the expansion of the universe is not like shrapnel flying from an explosion. It's like the rising of dough, with raisins embedded in it. Each raisin sees every other one moving away, not because any single raisin is special, but because the dough itself is growing, and every part of it shares in that motion equally, including yours. And yet, this doesn't mean you're lost in the margins, because margins require edges, and edges require a shape that the universe does not seem to have. The observable universe, the part we can see, is limited only by the speed of light and the age of the cosmos, not by any kind of cosmic boundary wall or border fence. And beyond that horizon is more space, more galaxies, more of everything, meaning our position is not at the center of the whole thing, but neither is it on the outskirts, because in a universe that might be infinite, or even just very, very large and curved in ways our minds struggle to picture, the idea of center loses its meaning altogether. So when we say you are not at the center, we're not trying to take something away, we're offering something deeper. You are a part of a vast expanding structure that treats all its locations equally, a universe that doesn't revolve around you, but includes you fully, without putting you above or beneath anything else. And this equality isn't just philosophical. It's written into the very physics of space itself, into the way galaxies move, into the maps of cosmic microwave background radiation, into the large-scale structure of the universe, which looks statistically the same no matter where you take your measurements. A feature called homogeneity and isotropy, which means uniformity across all directions and all places. And the beauty of this symmetry is that it humbles you without erasing you. It reminds you that while you are not the axis of reality, you are still on the canvas, still stitched into the expanding fabric of everything, still floating in a position that is just as legitimate as any other. And once you stop thinking in terms of middle versus edge, you start seeing the universe as a whole where every point gets to participate. Not as a king or a servant, but as a thread in the same tapestry. And you might ask, then, how we measure our position at all? What does it mean to say we're somewhere if there's no up or down, no central dot, no cosmic compass pointing home? The answer is subtle. We define our position only in relation to other things, because there is no absolute grid in space, no invisible coordinate system hanging in the void, only distances and motions and the fabric they ride on. And this is why even Einstein redefined gravity not as a force between objects, but as the curvature of space and time caused by mass and energy, because everything, including you, exists not in an empty arena but on a playing field that bends and stretches and flows, and you are inside it, not floating above it. So instead of trying to pin down where the center is, physicists began asking different questions. How old is the universe from this point? What can we see from here? How far can light have traveled since the beginning? And these questions build a picture of the observable universe around each observer, making it seem like everyone is at the center of their own bubble. Not because the universe is lying to them, but because expansion looks the same from everywhere. So each view becomes a unique snapshot of a much larger whole. And here's where things get more poetic. Because every point is equally valid, the experience of the universe becomes more democratic, more communal, more deeply shared, and your place in it, while not specially chosen, is still wondrously connected. As if the universe doesn't need a center, because it's structured so that meaning comes from the inside out. Not from where you stand, but from what you are aware of, and how deeply you understand your own participation in the cosmic story. And this changes how you see yourself, no longer a tiny speck lost on the fringe of everything, but a witness to an unfolding that doesn't need a favored location to be miraculous. A traveler inside a story that treats every position as one more place for the universe to reveal itself. And maybe that's the secret hiding in plain sight. You don't need to be at the center to be central to something, because the center isn't a position, it's a perspective. And once you let go of the idea that someone else's viewpoint matters more than yours, because of where they're standing, you begin to realize that you, too, are woven into the pattern, that your gaze, your thoughts, your sense of awe, all have equal footing with anyone else in the cosmos, from distant galaxies to neighboring stars, because location does not grant importance. Participation does. And the more deeply you engage with the wonder of existence, the more central you become to the only story that truly matters. The one unfolding from your eyes, through your questions, into the vastness that surrounds you, not asking for permission to matter, but quietly realizing you already do. Galaxies aren't flying away, space is growing between them. When you look up at the stars and think about distant galaxies drifting away, it's natural to imagine them as little islands floating off into a dark cosmic ocean, sailing farther and farther from each other, like boats losing sight of land. But that image, while easy to picture, is not what's really happening, because galaxies aren't actually flying away through space the way a rocket leaves Earth or a bird soars through air. They're mostly staying still, while the very space between them is stretching, expanding like dough rising in an oven, making the distances grow, not because the galaxies are racing outward, but because the cosmic fabric beneath them is gently pulling apart. And this idea may sound strange at first, especially if you've always thought of the universe like a room filled with moving objects. But in truth, it's more like a living stage where the floor itself expands, while the actors stay where they are. So what we see as motion is really the space doing the moving, not the galaxies themselves. And that's a huge difference, because it changes how we understand everything from the way light travels to how the cosmos will evolve in the future. To see this clearly, imagine two ants standing on a stretchy rubber band, both holding still. But then someone starts pulling the rubber band from both ends, and over time the ants find themselves farther apart, even though they haven't walked a single step. This is what's happening on the grandest scale imaginable, not with ants, but with entire galaxies, and not with a rubber band, but with the very geometry of space, which is not as fixed as we once thought, but flexible, dynamic, and growing. And this idea isn't just a metaphor, it's backed by real measurements, because when we observe distant galaxies, we notice something called redshift, where the light they emit gets stretched to longer, redder wavelengths, not because the galaxies are moving away like a car driving off with its headlights on, but because the space between us and them is expanding during the light's journey, lengthening the wave itself as if the universe were gently tugging on it with invisible hands. And the farther away a galaxy is, the more its light has been stretched, meaning we're not just seeing objects in motion, we're seeing the effects of a growing universe, one that pushes space itself outward, changing the very paths that light and time follow. And here's something even more mind-bending. This expansion isn't powered by galaxies pushing against anything, or by energy coming from a central explosion, but by the properties of space itself, especially something called dark energy, which seems to fill all of space and causes it to stretch more and more over time, even in the emptiest places where no matter exists at all. And because of this, the expansion doesn't need things to move, it just needs space to exist. And where space exists, stretching follows now. This stretching isn't noticeable on small scales, like within our solar system or even our galaxy, because gravity is strong enough to hold those structures tightly bound together. But on the scale of millions or billions of light years, the gravitational glue becomes too weak, and the stretching of space takes over, pulling vast clusters of galaxies farther and farther apart, not by shoving them, but by increasing the fabric between them, like marks drawn on the surface of a balloon that grows as you blow air into it. And this is why, when astronomers mapped the motion of galaxies, they didn't just see a few things drifting here and there. They saw a pattern, one that made it clear something fundamental was happening. The space between all galaxies was growing in every direction evenly, smoothly, and the further you looked, the faster the growth appeared, as if the universe were quietly lifting all points away from each other, without favor or bias, like a tide rising beneath ships, rather than a current dragging them across the sea. And the implications of this are enormous, because it means the universe has no center of expansion, and every galaxy, no matter how distant, sees other galaxies moving away in the same way. Not because everything is exploding outward, but because the universe is unfolding from within itself, generating more space in every direction, carrying galaxies along like raisins embedded in rising bread dough. And this understanding reshapes the story of cosmic evolution. We are not watching galaxies escape some ancient explosion. We are witnessing the quiet but relentless growth of the very container they rest in. A container with no walls, no edge, and no outside. And perhaps the most astonishing part is that this expansion doesn't require energy in the way an explosion does. It's not something that needs to be maintained by a fire burning at the core. It's a natural feature of the equations that describe our universe, a solution to the shape of space and time itself. And once it started, it didn't stop, and may never stop. Because space can stretch without resistance, without friction, without dragging anything behind it. And this is what allows galaxies to remain still while moving apart. What allows the past to remain visible while shifting further into the distance. What makes the night sky not just a canvas of stars, but a living map of a universe in motion through growth, not flight. And as you absorb this, a subtle truth becomes clear. The galaxies are not fleeing from you. They are being carried by the same fabric that carries you. They are held still on a platform that stretches beneath both of you, and your sense of motion comes not from the galaxies themselves, but from the way light travels across the swelling distances. So when we say galaxies are receding, what we mean is that the ruler we use to measure distance is growing, and that growth creates the illusion of motion. Just as 2 points on an inflating balloon seem to drift apart, even though they haven't changed positions relative to the surface they live on. And all of this leads to a question that stirs the heart of cosmology. If space keeps growing, what will happen in the far future? And the answer is both beautiful and lonely. The galaxies we see today will one day slip beyond our view. Not because they've moved faster than light, but because the space between us and them will stretch so quickly that their light will never reach us again, and the sky will grow darker, quieter. Not because the universe is dying, but because it is growing faster than light can cross its own distance. And this, too, is not fiction, but the real, measurable fate of expansion, written in equations, confirmed by telescopes, and unfolding slowly with every passing second. So the next time you hear someone say that galaxies are flying away, gently correct them, not with pride, but with wonder, and explain that what's truly happening is even more remarkable. The galaxies aren't going anywhere, but the space between us is changing, growing, expanding like a silent breath. And we are all riding that breath together, not as travelers leaving each other, but as passengers drifting calmly apart on a growing sea that has no shore. The universe doesn't grow into something. It creates space as it expands. When most people imagine the expanding universe, they picture it as something blowing up inside a vast empty container, like a balloon swelling inside a room or ink spreading in a glass of water. But what if the truth is far more mysterious and far more beautiful? That the universe isn't growing into anything at all, because space itself isn't moving into a larger space. It's creating space as it expands, unfolding the stage as the play goes on, building the canvas as the painting stretches outward. And this isn't just poetic thinking. It's one of the most fundamental, misunderstood truths in modern cosmology. Because the expansion of the universe is not like a balloon growing inside a bigger room. It's like the surface of the balloon itself, becoming larger, where there is no external space to fill, no pre-existing void waiting to be occupied. Only the universe making more room within itself. And this idea may sound strange because everything in your daily life exists within something else. Clouds in the sky, water in a cup, your body in a room. But the universe breaks this rule. It has no outside, no border, no backdrop. And trying to imagine what it is expanding into is like asking what's north of the North Pole. Because the concept only makes sense if you assume there is something beyond. But in this case, there simply isn't. And when cosmologists say the universe is expanding, they don't mean it's moving outward through space. They mean that the amount of space between things is increasing, not into something, but from itself. And this has been confirmed again and again by careful measurements of light from distant galaxies, by the discovery of cosmic background radiation, and by the mathematics of general relativity, which allows for a universe that doesn't need an outside to grow, a model in which space and time are part of the system, not sitting inside a bigger one. And this is why there's no cosmic wall to crash into, no outer layer to reach, no center to depart from, because the expansion happens everywhere, not from a point, and not toward a destination, but within the fabric of space itself, a gentle stretching that occurs in all directions from every location equally, creating more space, rather than pushing into old space. And this is one of the hardest things for the human mind to grasp. Because we evolved to think locally, to touch and move through space, to imagine rooms, borders, and containers. But the universe doesn't play by those rules. It writes its own, and one of them is this: space is not a stage. It's part of the act. And perhaps the most powerful metaphor comes not from explosions or balloons, but from baking. Imagine a loaf of raisin bread in the oven. And as the dough rises, the raisins move away from each other. Not because they're traveling, but because the dough itself is swelling. And now imagine that the bread is not inside an oven at all, that the dough is all there is, and that it makes more dough as it grows, not expanding into a kitchen, but growing the kitchen itself, piece by piece, as it stretches. And suddenly, you begin to understand what it means for the universe to create space rather than occupy it. And this leads to deep questions. If the universe is expanding, what came before? Where did it begin? What's outside it now? But the answers are not what you'd expect. Because the beginning of the universe wasn't an explosion in space. It was the birth of space, and time, and energy all at once. And if you ask what was outside or before that, you are using words that only make sense inside the universe. Words that break down when applied to something beyond. Because there may be no beyond. No before, only a starting point that contains its own dimensions, and grows not by invading a larger area, but by producing new area, as if a city built itself outward with no land to build on, making new land as it laid bricks, adding more sidewalk and sky with each step forward. And this is not just a philosophical trick. It has real consequences for physics, for how light travels, how galaxies move, how the age and size of the universe are calculated. Because if the universe were expanding into a surrounding void, there would be edges, boundaries, frontiers, but there are none, only horizons, limits on what we can see, not because there is a wall, but because light has only had so much time to reach us. And as time goes on, that horizon grows, letting us see more. Not because the universe is opening up like a curtain, but because space is being added, and with it, more moments of visibility unfold. And this concept becomes even more powerful when you realize that this process is still happening, that the space between galaxies is growing more every second, and that it's not being filled in from the sides, it's being woven from within, like new thread forming between stars. And while this might sound mystical, it's grounded in math, in observation, in the redshift of light from ancient galaxies, in the patterns of leftover heat from the early universe, in the frameworks built by physicists over the past century, all converging on a single truth, that expansion is not movement through space, but the creation of space itself. And when you absorb this fully, it changes the way you view distance. Because distance itself is not fixed, it is fluid, it stretches with time. And this is why some galaxies we observe today appear to be receding faster than light. Not because they breaking any cosmic speed limit, but because the space between us and them is growing so fast that even light can't catch up. And this doesn't violate relativity, it proves it, because relativity governs motion within space, not the growth of space itself. And so the universe can keep growing forever, not into anything, but into more of itself, not as a firework exploding into emptiness, but as a process that multiplies the room in which everything exists. And in doing so, it forces us to rethink one of the most basic assumptions we make every day, that things need somewhere to go. Because in cosmology, things can stretch without going anywhere, and space can unfold without entering anything larger than itself. And perhaps that's the most humbling realization of all, that we are living not in a room, not in a box floating inside a bigger box, but in a reality that builds its own boundaries as it breathes. And as it breathes, it carries us with it, not outward, but inward, to a deeper understanding that expansion is not movement but becoming, and becoming doesn't need a container. It just needs possibility. So the next time someone asks where the universe is growing into, you can smile and answer with clarity. It isn't growing into anything, it's growing everything, including the space between atoms, the space between galaxies, and the space between every question you ask and the answer that is still forming, carried forward by the quiet miracle that space and time and the universe itself are not passengers on a journey through something else, but the journey itself still unfolding. Space itself is expanding, not objects moving through it. If you've ever watched a car drive away or a bird fly across the sky, your brain has learned to connect the idea of movement with objects changing position inside a fixed space. But when it comes to the universe, that everyday idea quietly breaks down because the galaxies we see drifting farther and farther apart aren't actually speeding through space like rockets. It's the space between them that's stretching, growing larger on its own, and that shift in perspective changes everything. Because it means the expansion of the universe isn't a race through the cosmos, but a reshaping of the cosmos itself, where the distances grow not because things are flying, but because the very ruler we measure them with is getting longer. This is one of those truths that sounds simple on the surface, but turns everything upside down once you really understand it, because it means you are not watching a grand cosmic explosion where pieces shoot outward into the void. You are living inside a reality where the fabric of space itself is expanding underneath your feet and all around you, and the galaxies appear to move away, not because they are traveling through space like boats on an ocean, but because the ocean is swelling between them, gently increasing the separation without requiring any actual motion at all. To see this more clearly, imagine two dots drawn on a balloon, and as the balloon inflates, the dots grow farther apart. Even though neither one moves across the surface, they're simply carried by the stretching of the surface itself. And now imagine you're standing on one of those dots, looking out, and every other dot is receding from you, not because they're rushing away, but because the surface they rest on is growing. And that's what space is doing in our universe, stretching in every direction, everywhere at once, not into something else, but from itself. And in doing so, it gives the illusion that everything is moving, when really the only thing changing is the space between. And here's where it gets even more fascinating. This expansion is not something you can feel locally, not something you can watch unfold on a human scale, because the forces that bind things together, like gravity inside galaxies or atoms inside your body, are strong enough to resist it. So your room isn't growing, your planet isn't stretching, your hands aren't drifting apart, but on scales of millions or billions of light years, the gentle 2G of this expansion becomes stronger than the pull of gravity. And that is where galaxies begin to drift apart, not because they're being flung outward, but because the floor underneath them is growing longer every second, not just from one side, but evenly in all directions. And this is not science fiction, it's something we've observed, measured, and modeled through decades of astronomical data, from the redshifting of light to the cosmic microwave background. And the most consistent explanation for what we see is that space itself is not a passive arena, but a dynamic, flexible thing, capable of growing, changing, evolving, not just as a backdrop, but as an active participant in the universe's story. And once you understand that space is not just the setting, but a character in the play, the whole structure of cosmology begins to make more sense. It explains why galaxies aren't getting farther apart, because they're accelerating through space, but because the distance between them is being stretched, like the numbers on a measuring tape that keeps growing, even while the numbers themselves don't move. And this shift in understanding helps us resolve paradoxes, like how some galaxies appear to recede faster than the speed of light, not because they're breaking physics, but because the space between us is stretching so quickly that their light simply can't close the gap. And this stretching doesn't require them to move at all, only the space itself to grow. And that kind of motion, or really, that kind of change, is allowed by Einstein's theory of general relativity, which tells us that the geometry of space is tied to energy and matter and time, and that space is not static, but bendable and stretchable. And when you give it the right ingredients, it responds by expanding. And this brings up a deep idea: the difference between motion through space and motion of space. A concept subtle enough to confuse even experts when first learning it. Because in most situations we encounter, movement happens inside a fixed container, like a ball rolling across a table. But in cosmology, the table itself is growing longer under the ball, and the ball may not need to roll at all to get farther away. And once you accept this, you begin to see why the distances between galaxies increase without requiring them to have propulsion or direction. Why the early universe didn't explode outward from a center, but expanded uniformly everywhere at once. And why there is no center of the universe today. Not because we haven't found it, but because there is none. Not in the way we usually define such things, because space doesn't expand from a location. It expands as a whole, and this type of expansion means that no matter where you are, the universe looks similar, and every observer sees distant galaxies receding. Not because they are racing past some fixed boundary, but because space is stretching evenly around all points. And this leads to questions that shake your intuition. If space is expanding, what causes it? Where does the new space come from? Is something being added? And the surprising answer is that space isn't being made from raw material. It's not filling a container. It's growing from the rules that govern its structure. rules built into the laws of physics themselves. And this process doesn't require a cause in the traditional sense. It simply happens as part of the evolution of the universe's geometry, triggered by conditions like dark energy, which acts not as a pushing force, but as a property of space that makes it stretch more over time. And we don't fully understand it yet, but we see its effects everywhere we look. Not just in deep sky surveys, but in the very fact that galaxies beyond a certain distance are no longer visible. Not because they're hiding, but because the space between us has grown faster than light could cross. And that's not a statement about speed, it's a statement about space itself expanding beneath the light, carrying those galaxies beyond our reach. And so, the takeaway is simple but profound. Galaxies don't need to move through space to get farther apart, because the space between them is doing the moving, and the more you study this, the more you realize how much of your intuition comes from living in a world where space seems solid, fixed, and passive, when in fact it's more like a fabric that stretches when pulled. And in our universe, something is always pulling, not from the outside, but from within. And this changes how we see our place in the cosmos. We are not passengers on objects flying through an empty hallway. We are part of a growing structure built into the fabric that stretches not toward anything but from itself. And that realization doesn't just explain the stars, it transforms how you think about movement, about distance, about what it means to be separate or connected. And it invites you to see the universe not as a vast place of flying objects, but as a living system where change comes not from travel, but from transformation. Not from going, but from growing. The observable universe is not the whole universe. When you look up at the night sky and see stars twinkling back at you from unimaginable distances, it is easy to believe you're seeing everything there is, like a full picture painted across the sky. But what if that glowing canvas is only the part you're allowed to see? Not because someone is hiding the rest, but because the universe itself has a built-in limit to how far light has had time to travel since everything began. Meaning the observable universe is not the full universe. It's just the part that fits inside our cosmic bubble of vision, defined not by the size of all space, but by the age of time and the speed of light. And this boundary, called the cosmic horizon, is not a wall or an edge, but a gentle limit drawn by time itself, because light takes time to move, and the universe has only existed for so many billions of years. We can only see as far as light has had time to reach us since the very beginning, which turns out to be about 46 billion light years in every direction, forming a sphere around Earth, not because we are special, but because every observer sees their own bubble of visibility. And this idea changes everything, because it means there could be, and almost certainly is, far more beyond what we can observe, possibly infinitely more. And yet it remains forever outside our view, not due to distance alone, but because space has been stretching as light travels through it, pulling galaxies farther apart, and in many cases, expanding faster than light can keep up. So even though some distant galaxy may have once been visible, the growing space between has now pushed its light out of reach. And that means entire regions of the universe could exist right now with stars, planets, even galaxies as real and vast as ours. And we will never know they exist, not because they're hidden behind something, but because the light from them has not and will not ever reach us, no matter how long we wait. And this isn't speculation. It's baked into the math of cosmology, and confirmed by observation, because the structure of space and the nature of light impose a kind of gentle blindness on all observers, giving each of us a personal cosmic horizon, a limit not of imagination, but of reach. And this leads to one of the most humbling realizations in all of science. The universe is likely far larger than we can ever detect, perhaps even infinite. And yet we are forever confined to our own glowing bubble of knowledge, surrounded by darkness, not because the darkness is empty, but because it lies beyond our ability to see, beyond the speed of light, and beyond the reach of time. And what makes this even more profound is that this limit isn't something we can move toward or travel across, because it's not a location in space. It's a limit in time. if we existed for another 100 billion years, we would still not be able to reach beyond it, because the boundary itself is also receding, as the space between galaxies grows faster than any spacecraft could ever cross. So the horizon moves with us, and parts of the universe keep slipping beyond it, like ships drifting over the curve of the ocean, no longer visible but still sailing onward. And once you understand this, you realize the observable universe is not the universe. It is just our pocket of the whole, just a single light bubble in a sea of other possibilities. And this has deep consequences, not only for how we see our place in the cosmos, but for how we think about truth. Because any idea we have about the universe, its size, its structure, even its fate, is filtered through this limited view, a view bounded not by ignorance, but by physics. And yet, even with this limitation, we can infer more, because the part we can see is astonishingly uniform, showing the same patterns and laws in all directions, suggesting that the parts we cannot see may follow similar rules. And that allows cosmologists to make educated guesses about what lies beyond, including the idea that our observable patch is just one of many, stitched together into a larger quilt of existence, where the universe doesn't have one center, but many centers of observation, each as valid as the next. And this removes the illusion that we are at the middle of anything, reminding us that every perspective is local, every horizon is personal, and yet every one of them is equally real, equally right, and equally limited, because it suggests that even our most powerful telescopes, which can peer back nearly to the birth of the cosmos, are still looking at just a sliver, a single window, a house whose rooms stretch far beyond our reach. And if the house is infinite, then no matter how many windows we look through, we will never see it all, not even a fraction. And yet, the room we're in is enough to give us meaning, enough to give us laws, particles, galaxies, and consciousness, all within this tiny fraction we call the observable universe, a cosmic island in an endless sea of potential reality. And this changes how you think about existence, because if we are just one patch of many, and if each patch contains its own galaxies, then we are not the center of the universe, not even close. We are a speck in a possibility that may stretch forever. And if that doesn't make you pause and rethink your place in everything, then think of this. There may be other regions of the universe so distant, so separate, that they follow slightly different rules, where constants like gravity or the charge of an electron vary just enough to make their world strange or even uninhabitable. And if our observable region is one of many, and the larger universe includes endless variations, then we are not just small, we are rare, a bubble where life can exist, where stars can form, where eyes can open and look out. And that adds a kind of beauty to our blindness, because even though we cannot see beyond our edge, we can still wonder, still imagine, and still build models of what might lie past the curtain. And that makes science not a cage, but a ladder, one we climb even though we know the ceiling may always stay out of view. And so the next time you look up at the stars and feel like you're seeing everything, remember this: you are only seeing what light has allowed, what time has permitted, and what physics has offered. And beyond that, beyond the edge of light, is a universe that doesn't disappear. It just quietly waits, forever beyond our touch, but never beyond our questions. Spacetime isn't a container, it's an emergent property. Most people imagine space and time as the stage on which the universe happens, like a giant invisible box where stars float, planets spin, and everything plays out inside a pre-built arena. But what if space and time are not the backdrop at all, not something the universe happens inside, but something the universe creates as it goes? Not a container holding events, but an outcome of them, something that forms because of what exists and how it interacts. And this changes everything, because it means the universe didn't start in space and time. It brought them into existence as it evolved. And that idea, as strange as it sounds, is not science fiction, like a ripple that forms on water, not because the ripple existed first, but because something else disturbed the surface. And in the case of space-time, the disturbance might be the energy, information, or quantum interactions of the universe itself. giving rise to space and time the way heat gives rise to temperature, or the way molecules give rise to pressure. And this might be the most important shift in understanding, since Einstein showed us that space and time were connected. Because now we are learning they might not even be the deepest layer, and to grasp this better, think of a video game, where a character walks through a 3D world. But the world doesn't exist independently. It is generated by code, rendered in real time based on rules and input. And the character feels like they move through space, but it's all an illusion created by underlying processes. And in a similar way, space-time might be the rendered surface of something deeper, something not built from distance or seconds, but from relationships, states, and changes. And this is not just a poetic metaphor. It's supported by serious attempts in theoretical physics to derive space-time from more basic ingredients, like quantum entanglement or information theory, which suggests that what we call here or now might just be patterns in how information is organized. And space is not the gap between things, but a way to describe how things relate, how cause leads to effect, and how events unfold. And one of the strongest clues for this comes from black holes, which seem to encode information on their surface, rather than inside, hinting that our 3D experience of space might be a projection of a more fundamental 2D structure. And this leads to the idea that space-time, with all its curves and distances and flows, is not the canvas, but the painting, not the platform, but the illusion created by what happens on the platform. And that illusion is powerful, so powerful that we treat it as real, because it behaves predictably, bends with gravity, carries light, and lets us build everything from maps to memories on top of it. And yet, behind that familiar experience might be something stranger, a reality where space is not a thing but a feeling, where time is not a line but a sequence of updates, like frames in a movie, and where nothing has location until it interacts, and nothing has order until it is observed. And this view doesn't just come from philosophy, it's being tested in the math of loop quantum gravity, string theory, and emergent gravity models, all of which try to rebuild the universe from ingredients that do not start with space or time, but end up creating them. And if that's true, it means our deepest intuition, that we live in a container called space, and move through a river called time, is only half the story, a useful story, but one that breaks down at the edges, especially near the Big Bang, or inside black holes, or in the quantum world, where space becomes grainy and time seems to vanish. And this also means that asking where the universe began might be a flawed question, because there was nowhere before the universe, since where only exists after space-time emerges. And just like asking what's north of the North Pole doesn't make sense, asking what the universe expanded into might also be missing the point, because space is not the room the universe is inside, it is the room the universe builds as it exists. And the same goes for time. It may not tick in the background, but arise from change, from entropy, from the growth of complexity, from the way things move and interact. And that would mean the past and future aren't destinations, but descriptions of how one pattern becomes another. And so, when we look around and feel like we are moving through space and living through time, what we're really doing might be participating in a dynamic unfolding, where the stage is built as the play goes on, and every moment is a new update to the code that creates the world. And this has profound consequences, because it means nothing is fixed, not even the thing we thought was most fixed, the structure of reality itself. And it could also mean that if space-time is emergent, then maybe consciousness is too, or maybe not. Maybe they are connected. Maybe the emergence of time is tied to awareness, or to measurement, or to information being processed. And some theories even suggest that the flow of time we feel is the result of our own brain stitching together events, constructing a narrative from discrete slices of change. And if space and time are emergent, they may not be the same for every observer, especially near extreme environments like black holes, where time slows and space twists, or at the quantum scale, where simultaneity becomes fuzzy and location is a probability, not a point. And this all points to a truth, that challenges our most basic assumptions. That the world is not made inside a room, but that the room is made by the world. And as we try to zoom in deeper, past atoms, past particles, past even the vacuum of space, we may find that the bedrock of reality is not space, not time, but something else entirely, something more abstract, maybe even more elegant, like a network of relations, a dance of values, a system of computation, or logic, or causality, and space and time are what those patterns look like when you zoom out. And that's why physicists talk about the geometry of space-time. Because geometry is a language for describing relations, not things. And if all of this feels like your mind is stretching, then good. Because that's what the edge of knowledge feels like. Not comfortable, not simple, but honest. And once you see space-time not as a thing, but as a story being told by the universe to itself, then suddenly, everything becomes more alive, more mysterious. Because we are not passengers riding through space and time, we are part of the process that makes them real. Redshift as proof that space is stretching. Imagine pointing a telescope into the dark sky and seeing not just stars or galaxies, but ancient light traveling toward you, carrying with it the faintest whisper of something extraordinary. Not just where it came from, but how the universe itself has changed while that light was on its way to you. And this change is not a guess. It's not a feeling. It's something we can measure, something called redshift. And though the name sounds simple, what it reveals is one of the most profound clues we have that space itself is stretching. Not that galaxies are just moving through space like cars on a highway, but that the highway itself is growing longer between them. And this idea can feel strange at first, because in everyday life, we're used to movement happening in space. Not space itself doing the moving, but redshift gives us a way to see that something deeper is going on. And to understand it, you first need to know that light behaves like a wave, with peaks and valleys. And each color has its own wavelength, with blue light having shorter waves, and red light having longer ones. And when an object is moving away from you, the waves it sends get stretched out, like the deepening pitch of a siren speeding away. And this stretching shifts the light toward the red end of the spectrum, hence the term redshift. And while this happens with any object that's receding, the redshift we see in distant galaxies isn't because they're moving through space in the usual way. It's because the space between us and them is expanding, stretching the light itself during its journey, like drawing dots on a balloon and watching them grow farther apart as the balloon inflates. But here's the fascinating part. In the balloon example, the dots don't move on their own. It's the surface that expands, and that's closer to what's happening in the cosmos. The galaxies aren't flying away like rockets. They're mostly staying still relative to their local surroundings. But the space between everything is increasing, and light that travels through that stretching space gets stretched too. So even if a galaxy hasn't fired any engines, its light arrives to us redder than when it left. Not because of motion, but because of cosmic expansion. And we can measure this redshift with incredible precision by looking at the specific fingerprints of elements in a galaxy's light, like hydrogen or helium, and seeing how much they've been shifted toward red. And the further a galaxy is, the more its light is redshifted. Not because it's going faster, but because the universe has had more time to stretch in between. And this led to one of the most important discoveries in science, that the universe is expanding, not from a central explosion, but uniformly in all directions. And redshift is the key that unlocked this realization. And it gets even stranger because when we plot the redshift of galaxies against their distance, we see a clear pattern, now called Hubble's law, which says that the farther away a galaxy is, the faster it appears to be moving away. But again, this speed is not from actual movement through space. It's from the expansion of space itself. And this difference matters, because it means there's no center, no privileged location, no edge from which everything exploded outward. Instead, every point in the universe observes other points moving away, just as you would see dots on a balloon drift apart no matter where you stood on its surface. And this makes Redshift not just a tool for measuring motion, but a window into the structure of reality. Because it shows us that distance is not fixed, that space is not rigid, but elastic, changing, stretching. Not because of something outside pulling it, but because of something inherent in the fabric of the universe. And this brings us to dark energy, a mysterious force that seems to be driving the expansion faster and faster, not slowing it down as we once expected. And the evidence for this too is rooted in Redshift. Because when we look at distant supernovae, exploding stars, we can use them as cosmic yardsticks to measure how far their light has traveled and how redshifted it has become. And the results stunned scientists, because they showed that the universe isn't just expanding, it's accelerating, and that something, perhaps dark energy, is pushing space apart with increasing intensity. And all of this understanding, from cosmic expansion to accelerating growth, comes from carefully reading the language of Redshift, from watching how light changes across vast distances, from treating photons like messengers that stretch as space stretches. And this means light doesn't just tell us about where it came from. It tells us what space did while the light was in transit, like a letter that grows longer while being mailed, because the road it traveled on was being built underneath it as it moved. And that's why Redshift is so powerful. It's not just a shift in color, it's a shift in meaning, in understanding, in perspective, because once you grasp that Redshift is evidence of stretching space, you realize that everything in the universe is involved in this quiet transformation, even if you can't feel it in your room or in your hand, because the expansion is on scales far beyond human experience. But light from distant galaxies brings it to us, allows us to see a slow, silent change in the very structure of reality. And when we measure that light, we're not just doing astronomy, we're doing archaeology of the cosmos, unearthing how the universe grew, how it changed, how it's still changing, and Redshift is the ruler we use to trace that journey. To draw a map not of things, but of spacetime itself. And this map tells us that everything we see is getting farther apart, not by force, but by nature, by the way the universe works at its core. And that realization turns every star into a signal, every galaxy into a clue, and every faint photon into proof that the cosmos is not still, but always unfolding, always stretching, always whispering the story of its own expansion. Hubble's law: the farther you look, the faster it recedes. If you could step outside the universe and look at everything from above, you might expect to find a pattern that shows a center, a direction, maybe some galaxies moving faster than others because of where they started or how old they are. But what astronomers actually discovered is far more surprising. And it all began when a man named Edwin Hubble pointed his telescope at the night sky and noticed something strange. Almost every galaxy he observed seemed to be moving away from us. Not just drifting a little, but speeding away, and not at random speeds, but in a very specific pattern where the farther away a galaxy is, the faster it seems to be retreating. And this wasn't just a curious observation. It turned out to be the foundation of a law that would change how we understand the universe itself. A rule now known as Hubble's law, which states simply that the velocity at which a galaxy moves away from us is directly proportional to its distance from us. Meaning, if a galaxy is twice as far, it is receding twice as fast. And if it is 10 times as far, it is moving away 10 times as fast. And this pattern holds everywhere we look, not because galaxies are racing away through empty space like runners on a track, but because the space between galaxies is expanding, carrying them along like raisins in rising bread dough. And what Hubble observed wasn't just motion, it was the whisper of a living, growing cosmos, one that isn't static or fixed, but one that stretches in every direction at once. And the more you look into the distance, the more you are peering into the past. Because light takes time to travel. So distant galaxies show us how the universe used to be. And the farther that light has traveled, the more the universe has expanded during its journey, making those galaxies appear to move faster, not because they are trying to escape, but because the very stage they stand on is getting bigger. And this is what makes Hubble's discovery so beautiful. It turned the night sky from a still picture into a dynamic story, revealing that the universe is not frozen in time, but growing, evolving, shifting. And this growth isn't happening from a center outward, but equally in all directions, with no preferred spot, no cosmic capital. And this is why Hubble's law is not just about speed, but about understanding the shape of reality, because it tells us that space itself has a built-in rule of expansion, and this rule can be measured, graphed, and predicted. And when scientists plotted the velocities of galaxies against their distances, they didn't see chaos. They saw a straight line, a clean relationship that told them the universe had a rhythm, a law, something that could be described in numbers, and the slope of that line, known as the Hubble constant, became one of the most important numbers in cosmology, a value that helps us estimate the age of the universe, calculate distances to far-off galaxies, and understand the overall fate of everything. And even though the exact value of the Hubble constant has been debated and refined over time, the law itself remains a cornerstone, because it's not just about how fast galaxies are moving, but about how the universe behaves on the grandest scale. And when you understand this, you begin to see something truly profound, that every part of the cosmos is part of the same unfolding story, that no matter where you are, you would see the same pattern, galaxies moving away faster the farther you look. And that means there's no special point of origin, no center from which everything exploded, but rather a universe where every point is like every other point, equally valid, equally central. And Hubble's law is the mathematical expression of this truth, showing us that the universe doesn't expand like a balloon with air rushing outward from a valve, but like a rising loaf where the dough itself is growing, and every piece of it moves away from every other piece in proportion to its distance. And this realization has changed, not just astronomy but philosophy, because it challenges our instincts about motion and position, about what it means to be in one place versus another. And if you think about it, this law is really a mirror. It shows us our place not in space but in time, because the farther we look, the older the light and the faster the recession. So Hubble's law is like a clock written in starlight, telling us how long the universe has been expanding, how fast it has grown, and how it might evolve in the future. And the tools we use to study this expansion, spectrographs, telescopes, redshift measurements, are like archaeological brushes uncovering not ancient bones, but the bones of time itself. And through them, we've discovered not only that the universe is expanding, but that the rate of expansion might be changing, accelerating in fact, driven by something mysterious we call dark energy. And this too fits into the framework Hubble began to reveal. Because the farther we look, the faster galaxies recede. And when we compare the rate of expansion across time, we see that the universe's story is not just one of growth, but of increasing momentum. And this raises questions so deep, they almost become poetic. What is driving this expansion? Will it continue forever? Will galaxies eventually move so far apart we can no longer see them? Will the night sky someday grow dark? Not because stars die, but because they slip beyond the reach of light itself. And these questions all trace back to that original insight, to Hubble looking through a telescope and daring to believe what he saw. And this is the power of a law like his. It doesn't just describe what is, it opens doors to what might be. And in a way, it teaches us something quiet but important about knowledge itself, that sometimes the biggest truths are not the ones that shout, but the ones that whisper consistently, the ones that hold steady across the sky, painting a straight line through the stars and asking you to follow. Cosmic expansion happens equally in all directions. You might expect the universe to have a preferred direction, some invisible wind blowing galaxies one way more than another. But when astronomers look deep into space in every possible direction, they find something astonishing. No matter where they look, the story the universe tells is always the same, because the expansion of the cosmos is not one-sided or uneven. It happens equally in all directions, like the rising of a perfectly round balloon, or the swelling of bread dough that pushes every point away from every other point in a balanced, coordinated dance. And this simple but profound observation is what tells us that our universe is not lopsided or drifting towards something, but that it grows with a kind of fairness, a cosmic symmetry that holds everywhere at once. And the way scientists discovered this wasn't by just assuming it, but by measuring light from galaxies scattered across the night sky, checking the redshift in every direction, and finding the same pattern over and over again, where more distant galaxies appear to move away faster, not because they are actually flying through space faster in different places, but because space itself is growing steadily and symmetrically, and this matters more than it might seem at first. Because if expansion happened faster in some directions than others, it would suggest something is pulling, something is pushing, maybe some kind of central explosion or cosmic imbalance. But the fact that expansion is equal in all directions tells us something much deeper, that the universe is not stained, retching outward from a single center, but that the very fabric of reality is unfolding from every point at once. And that includes your point of view, because wherever you are in the universe, you would see the same thing. Galaxies rushing away faster the farther you look, not because you're special, but because space doesn't expand around a single anchor. It expands around every point equally. And this means the universe has no universal direction, no cosmic up or down or left or right, only relationships between objects that drift apart as space grows. And the precision of this symmetry is one of the great clues in modern cosmology, because it supports the idea that the universe, on large scales, is both homogeneous and isotropic. 2. Scientific words that simply mean it looks the same in every location and in every direction. And this might sound abstract, but it's actually what gives scientists confidence that the laws of physics are consistent, that what we learn in one corner of space applies in all corners, that the rules aren't changing as you go. And without this kind of uniform expansion, our models would fall apart, because gravity, light, and time would behave unpredictably, depending on where or when you were. But because expansion is equal in every direction, it suggests a deep order, a hidden logic that binds the universe together. And perhaps more beautifully, it shows us that there is no cosmic spotlight, no favored place, no privileged observer, because the same expansion seen from Earth would also be seen from a galaxy 10 billion light years away. And this raises a quiet but powerful idea, that there is no absolute center, no edge, no origin point that space is stretching from, but rather that every observer, no matter where they are, feels like they are at the center of expansion. Not because they are, but because the math and the physics make it so, and that is one of the strangest and most humbling truths of the universe. You are not the center of everything, but you are not off to the side either. Because in this model of the cosmos, everyone stands on equally expanding ground. And what this tells us is that the universe doesn't need a central motor to grow. It doesn't push from behind or pull from ahead. It simply grows everywhere. And the evidence of this is etched into the sky itself, in the light that travels from ancient galaxies and whispers the same message no matter where it comes from. And the reason this happens is because of how space behaves. It isn't a backdrop or a container. It's a dynamic entity that can stretch, bend, ripple, and grow. And when it expands, it carries galaxies along, like dust on the surface of a balloon. But the balloon is invisible, and you are on its surface, unable to see the full shape, only able to measure how far. Others have drifted away, and those measurements, when taken carefully in all directions, show no bias, no lean, no bulge, only a calm and steady rhythm of growth. And this rhythm is so consistent that even the leftover light from the early universe, the cosmic microwave background, shows the same evenness, the same balance, as if the whole universe had been tuned like a perfect drum before it began to play. And this evenness is so important that scientists call it the cosmological principle. The idea that on large scales, the universe is the same, no matter where you stand or where you look. And while this principle might not hold true inside small regions, like galaxies or solar systems, where gravity clumps matter into stars and planets and chaos reigns, it does seem to hold when you zoom far enough out, when you step back and look at the whole canvas. And what you see then is a pattern of gentle expansion in every direction, as if the universe is breathing out uniformly, without preference, without noise, just a smooth unfurling of space itself. And this smoothness lets us model the universe, predict its future, understand its past. Because it tells us that the growth of the cosmos is not random, not chaotic, but deeply ordered. And when you combine this knowledge with what we know about dark energy, the mysterious force accelerating this expansion, you begin to realize that not only is the universe growing equally in all directions, but it's doing so faster and faster, with no signs of slowing down. And yet still, even in this acceleration, the symmetry remains. The balance holds, and that tells us something extraordinary about the nature of reality. Something that even children can grasp if they listen closely, that the universe is fair in how it grows, fair in how it moves, fair in how it tells its story to every observer, no matter how far apart they are. And in that fairness, there is both mystery and comfort, because it means the laws that govern the stars also govern your body, your heartbeat, your breath, and the space between every atom in your hand. And though you may never see the whole universe, you can be certain that the part you stand in is not left out, not forgotten, because it too is part of the expansion, part of the rhythm, part of the great unfolding that happens, not just somewhere, but everywhere at once. Why the universe doesn't expand inside galaxies. If the entire universe is expanding, if space itself is stretching in all directions, then why don't galaxies stretch along with it like everything else supposedly does? And why isn't your body or the Earth or even the atoms inside you being pulled apart, slowly and silently, by the growth of the cosmos? It sounds like a simple question at first, almost childlike, as if you're imagining a cosmic balloon inflating and asking why the dots drawn on it don't get farther apart. But when you really stop to think about it, this question tugs at something deeper, a quiet confusion about what it actually means for space to expand, when everything around you appears so still and solid. And the answer, though rooted in physics, opens a door into understanding how motion, force, and balance shape the very structure of everything you call home. To understand this strange contradiction, that the universe is getting bigger, yet galaxies seem to stay the same, you have to first understand what the expansion of the universe actually is. Because it's not like things are flying outward through empty space, as if from a central explosion. Rather, space itself, the invisible stage that holds everything, is what's increasing, like a fabric being woven larger with every passing second. Not by adding more threads, but by stretching the ones that are already there. This stretching happens not to the galaxies, stars, or planets themselves, but to the space between clusters of galaxies, between gravitationally disconnected regions of the universe. And that subtle distinction changes everything, because galaxies are not just floating through nothingness like boats on water. They are gravitationally bound structures, where the internal pull of gravity is far stronger than the gentle outward push of cosmic expansion, which is too weak to tear apart anything that's held together tightly enough. Imagine you're holding hands with someone on an ice rink, while the ice slowly spreads in every direction. As long as your grip is firm, the ice can grow beneath your feet without pulling you apart. And that's what's happening with galaxies. Their gravity is like a strong grip that keeps all the stars dancing together, regardless of what the cosmic stage is doing underneath them. The expansion of space only becomes noticeable at vast scales where the pull of gravity no longer dominates, which is why galaxies can move away from each other as the universe grows. But stars within a single galaxy stay in orbit, locked in a kind of silent harmony that defies the larger cosmic trend. And this harmony is not fragile. It is robust, stable, and persistent over billions of years. Think of it like neighborhoods in a city. The city might be expanding, adding more space between districts, but the houses on your street don't stretch apart, and your own home doesn't grow wider with every year. It stays exactly as it is, because it is held together by nails, beams, and the laws of structure. And galaxies too are held together by gravity's architecture, which doesn't loosen with the passing of time. In fact, the gravitational glue inside galaxies is so powerful that even the mysterious push of dark energy, which accelerates the expansion of the universe on the largest scales, is almost entirely irrelevant within these structures. The stars orbiting the center of the Milky Way feel no significant effect from the universe's overall stretching, just as your heartbeat is not influenced by the slow drift of continents. This is why, even though space is expanding, the solar system, the Earth, your body, and even the particles inside atoms are all immune to that expansion. Not because they are special, but because they exist inside systems where other forces completely outweigh the influence of cosmic stretching. And, in this case, gravity is the guardian that keeps the chaos at bay. You might wonder then, if space is expanding all the time, why we don't see it happening in real time, why there is no gradual drifting apart of things in our everyday lives. But the truth is that expansion is like a silent whisper happening across unimaginable distances. It's not an explosion or a rip or a shift you can feel or hear, but rather a slow and continuous swelling of the cosmic stage that only becomes evident when you look at things billions of light years away, where light itself takes eons to reach us, revealing that galaxies are not just distant. They are growing more distant as the space between them gets longer, like taffy being pulled between fingers. This is why cosmologists study galaxy clusters, not individual galaxies, when trying to measure the universe's expansion, because that's where expansion leaves its fingerprint. In the increasing distance between unbound regions, not in the stable hearts of galaxies, where gravity stands its ground. Inside a galaxy, expansion is simply too weak to matter. It's like trying to blow apart a brick wall with a gentle breeze. And so the galaxy lives as a kind of island of stability in an ocean of growth, a quiet, stormless eye in the whirlwind of space. And here's something even more astonishing. The same physics that explains why galaxies resist expansion also helps us understand why the early universe formed stars and galaxies in the first place. Because if everything had expanded equally and forever, without any competing forces, nothing would have condensed into clusters, stars, or planets. And you wouldn't be here to ask these questions at all. The fact that galaxies can resist the universe's expansion is what makes structure possible. It is the counterbalance, the cosmic grip that holds the seeds of complexity together. This is why when we look out into the night sky, we don't see blurry, stretched galaxies that are being torn apart. We see organized spirals, glowing cores, and dancing stars that have been bound for billions of years, defying the emptiness and holding tight to one another. In this way, galaxies are not exceptions to the rule of expansion, but reminders that the universe is not a single smooth process. It is a layered and dynamic place where different scales of structure follow different rules, and where harmony can exist inside motion, where permanence can hide within impermanence. And perhaps the most beautiful part is this: even though everything is moving, even though the cosmos is stretching like a quiet breath that never ends, you are living in one of the pockets of stillness where things stay just as they are long enough to allow meaning, memory, and life to unfold. And that fragile stillness, protected by gravity, is what lets you look up at the stars and wonder not just where the universe is going, but why it lets anything stay at all. The speed of light limits how far we can see, not how far the universe goes. You might think that if you had a strong enough telescope, or enough time, or the right technology, you could eventually see everything in the universe. But no matter how clever we get, how sensitive our instruments become, or how far out we build our observatories, there is a fundamental wall we can never look beyond. Not because the universe ends there, but because light itself moves at a finite speed, and that speed sets the outer boundary of what we can ever witness, a kind of cosmic horizon drawn not by space itself but by time. Because light takes time to travel, and everything we see, from the moon to distant galaxies, is not seen as it is now, but as it was when its light first began the journey toward our eyes, which means that the farther out we look, the further back in time we peer, and at a certain distance, about 46 billion light-years in every direction, there is a limit, not because the universe stops there, but because the light from beyond that distance hasn't had enough time since the beginning of the universe to reach us yet. like a message trapped in a bottle that was thrown too late for us to ever read, which might sound simple at first, but grows stranger the deeper you explore, because the universe itself has been expanding the entire time that light has been traveling, stretching space between us and those ancient sources. So even though we can only see about 13.8 billion years back in time, the actual distance to the most distant objects we can observe today is much farther than 13.8 billion light years. Because while the light was traveling toward us, the universe was pulling the space it crossed farther apart, so that what was once near is now unimaginably far. And what is more, galaxies beyond that horizon didn't disappear. They still exist, they still move, they still evolve, but we will never ever see them. Because their light, even if it's trying to reach us now, is being dragged away by the stretching of space faster than it can travel toward us, which is not like a spaceship zooming off into the dark, but more like the ocean growing wider beneath a swimmer who's trying to reach you from the other shore. And this brings us to a humbling realization. The edge of the observable universe is not the edge of the universe itself. It's just the edge of what light has had time to deliver. So what we call the universe is, from our perspective, really just a bubble of visibility inside a vastness we cannot access. Not now, not ever. And this bubble is centered on us. Not because we're special, but because every observer in the universe carries their own bubble too. Meaning every conscious being anywhere, if they exist, has their own version of a visible cosmos that looks centered around them, like a flashlight beam shining out from their own position in space-time. And the strange part is, we don't actually know how large the entire universe is beyond that visible shell. It could be just slightly larger than what we can see, or it could be infinite, with entire galaxies, civilizations, maybe even cosmic phenomena we can't imagine lying forever out of reach. And that's not just poetic. It's a real scientific boundary that makes our position in the cosmos fundamentally limited, not because of where we are, but because of when we are, since we're seeing light that left objects billions of years ago, which makes our vision of the universe not just a view through space, but through time itself. And the deeper we look, the younger the universe was when that light was emitted. So much so that we can see the universe when it was only 380,000 years old, a mere baby in cosmic terms, glowing in the form of the cosmic microwave background radiation, which bathes the entire sky in a nearly perfect uniform glow, and serves as a kind of backdrop to all that followed. Yet beyond that, the light is blocked, not because there's a wall, but because the early universe was too hot and dense for light to travel freely. Meaning we can never see the Big Bang directly, only its fingerprints. And this leads to a subtle but powerful truth. Our understanding of the cosmos is shaped entirely by what light can show us. And there may be structures, events, even laws of physics that govern parts of the universe we can never detect, because their signals will never reach us. Not because they're weak, but because the medium itself, space, is expanding faster than their messengers can fly. And this expansion is not uniform in our view, but accelerates due to something we call dark energy, a mysterious force that's pushing the universe apart at an increasing rate, which means that more and more galaxies will slip beyond our horizon forever, their light stretched into invisibility, their stories severed from our timeline. So the observable universe is actually shrinking in terms of what we will one day be able to see, not growing. And in billions of years from now, future astronomers may live in a universe that appears empty. Not because it is, but because the light from everything else has faded beyond reach, and the cosmos will look like a lonely island, disconnected from its past and blind to its true scale. And if that sounds sad, it's also a powerful reminder of how precious our window in time is. How rare this moment is when we can still see the afterglow of the Big Bang, still trace the galaxies flying outward, still piece together the story of where we came from. And even though we can't see beyond the speed of light limit, we can imagine, we can calculate, and we can wonder, because science doesn't just stare at what's visible, it tries to sketch what's beyond the curtain, knowing it may never touch it. And that's perhaps the most beautiful part of all, that in a universe where we can never see everything, the desire to understand never fades. And that longing itself might be the most important light we carry, not one that travels through space, but through the mind, forever expanding. Why we'll never see most of the universe. You might think that with better telescopes, faster rockets, or just enough time, we could eventually see everything in the universe. But what if the truth is far stranger and far sadder than that no matter how advanced we become or how long we wait, there are vast regions of the cosmos we will never ever see, not because we're not clever enough or patient enough, but because the rules of the universe itself have already locked those places out of reach forever. And this isn't science fiction. This is what modern cosmology tells us, that as the universe expands, light from most galaxies will never have the chance to reach us. Not now, not in a billion years, not even in eternity, because space is growing faster than light can cross it, meaning entire sections of reality are drifting away into permanent invisibility, into a cosmic exile beyond our horizon. And the most unsettling part is this. Every second you're alive, more of the universe vanishes from view. Not because it ceases to exist, but because the universe is pulling it away from us faster than even light can keep up. To understand why this happens, we have to first accept something that feels almost magical, but is grounded in hard physics. Space itself is not just a stage where things happen. It can grow and stretch and change, and ever since the Big Bang, it's been expanding in all directions. Not like a balloon being blown up inside a room, but more like the room itself getting bigger with every passing moment, so that galaxies aren't flying through space like comets, but instead they're sitting mostly still, while the space between them and us stretches like elastic. That's why the farther we look, the faster galaxies seem to be moving away. Not because they're speeding off into the distance like cars on a highway, but because the road itself is getting longer under their wheels, and this has an incredible consequence. There's a limit to how far light can travel to reach us, a boundary known as the cosmic light horizon. And beyond that invisible wall, no photon will ever make it to our eyes, no matter how long we wait, because the space it must cross is expanding faster than it can move. And here's the catch. This isn't just a temporary limit like a fog that clears over time. It's a permanent barrier baked into the way the universe works. Imagine shining a flashlight across a river that's growing wider every second. Eventually, no matter how bright your beam is, the other side will slip so far away that your light will never reach it. And this is what's happening on a cosmic scale. Galaxies that used to be close enough to see will eventually move beyond our light horizon and disappear. Not because they turned off, but because the light they're still emitting is being stretched and weakened into nothingness before it can ever arrive. Even more mind bending is the fact that many of these galaxies are still there right now, full of stars and planets and perhaps even life. But from our point of view, they're already gone. We are, in a sense, surrounded by ghosts of a visible universe that is slowly fading into the dark. You live in a shrinking bubble of cosmic visibility, and every day that passes, that bubble gets smaller in terms of what it can eventually see, even though the actual universe is getting larger. Scientists estimate that right now, the observable universe is about 93 billion light-years wide, even though the universe itself is only 13.8 billion years old. And that number might sound contradictory, but it makes perfect sense when you remember that the space between things has been growing while the light has been traveling. So something that emitted its light 13 billion years ago might now be tens of billions of light years away. And yet, as far as we can tell, the entire universe might be infinite, or at least much, much bigger than the part we can ever observe, meaning that what we see is just a small sliver of what exists. But here's where things get even more haunting. Because of dark energy, the mysterious force that seems to be pushing the universe apart faster and faster, most galaxies are not just far away, they are accelerating away from us. This means that not only are we losing access to distant galaxies over time, but the rate at which we lose them is increasing. Billions of galaxies that we could see today will eventually slip away from our view like ships disappearing over a horizon they'll never return from. In the unimaginably far future, if intelligent beings exist in our galaxy, they might look out and see nothing but blackness beyond their own cluster of stars, not because the universe is empty, but because all the evidence of everything else has been pulled so far away that no signal remains, no message ever arrives, and no proof of the greater cosmos can be found. They will live in an island of stars, unaware that a grand universe ever existed outside their little patch of light. And we, right now, are among the few living creatures in cosmic history who exist at the perfect moment, when the universe is old enough to have formed galaxies, but still young enough for us to see them. We are living in a golden age of visibility, and we don't even realize it. Our telescopes, with all their limitations, are looking out into a disappearing frontier, and every new discovery is a glimpse into something that one day will be beyond reach forever. This isn't a limitation of technology or money or imagination. It is a fundamental consequence of the way space-time behaves, a reality that no spaceship, no signal, and no observer can outrun. You may have heard people say the sky is the limit, but in cosmology the limit is far worse. It's the edge of what can be seen. And beyond that, the light itself is denied access. What we know of the universe today is stitched together by photons that have been traveling for billions of years, stretched by cosmic expansion into microwaves, into radio waves, into faint whispers of what they once were. And every time you look at the stars, you're seeing the universe not as it is, but as it was, filtered through the cruel and beautiful geometry of an expanding cosmos. And so the truth is this: the universe is not only bigger than we can imagine, it's more unreachable than we care to admit. There will always be more that we cannot see than we can, more that remains hidden than is ever revealed. And no matter how far our science advances, there are entire regions of space that will stay invisible, not because of fog or dust or shadows, but because of the raw mathematical laws of the universe itself. We're not at the center of a visible sphere. We're sitting inside a shrinking spotlight of what light has managed to reach us in time. You are living in a window that is slowly closing, and the universe outside that window is still alive, still bright, still full of wonders we will never know. That is the tragedy and the poetry of a cosmos governed by expansion. It promises more than we can ever see, yet reveals just enough to make us ache for what lies forever beyond our reach. There's no edge to the universe, only a limit to what we can see. You might picture the universe like a giant balloon, stretching outward into some kind of surrounding space, with a clear edge where everything stops. But what if that idea is completely wrong, and the universe has no edge at all, no outer shell, no border you could touch even if you flew forever in one direction? Only a soft and strange limit to what your eyes can see, not because there's a wall blocking your view, but because light itself hasn't had enough time to reach you from the farthest parts of reality. This isn't just a poetic way of thinking. It's one of the most fascinating truths in modern science, that the cosmos may be endless or looped or curved in ways we can barely imagine. Yet our ability to observe it is forever restricted by the speed of light and the age of time itself. Meaning your map of the universe is not a map of everything that exists, but just of everything that has sent you a message quickly enough to arrive. Imagine you were standing in the middle of a vast field covered in fog, holding a flashlight and trying to see as far as possible. The light can only travel a certain distance before it fades into mist. Not because the field ends, but because your light just can't reach any further yet. This is what astronomers call the observable universe. A bubble of visibility around you, stretching about 46 billion light years in every direction. Not because that's where the universe ends, but because that's how far light has been able to travel since the universe began. That number might seem strange, especially when you consider that the universe is only about 13.8 billion years old. But that's where things get tricky, because while the light has been traveling, space itself has been expanding, stretching out like taffy, meaning the source of that ancient light is now far beyond the distance it originally had to cross. But let's step back for a second. What does it really mean for something to have no edge? When you look at a ball or a table or a book, it has clear sides, boundaries, ends, so your brain is used to thinking that everything must have an outer limit. But some things in nature don't work that way. Take Earth, for example. If you walk in one direction long enough, you don't fall off the edge. You end up back where you started, because Earth is curved in 3 dimensions. Now imagine a universe that's curved in higher dimensions, possibly even infinite, with no outer shell, no edge to touch, just more and more space, or possibly even a shape that loops back into itself, like the surface of a balloon or a donut, but in ways that are almost impossible to visualize. Scientists call this the geometry of space, and it's one of the most important ideas in cosmology. Depending on the total amount of matter and energy in the universe, space can be flat, like a table, curved like a saddle, or closed like a sphere. If it's flat, it can go on forever. If it's closed, you could theoretically travel in a straight line and eventually return to where you started, without ever finding a wall or boundary. But here's the twist. No matter which of these shapes the universe takes, we don't get to see all of it. We are locked inside a visual bubble, limited by light, time, and distance, and everything beyond that bubble remains forever out of view. This limit is not a physical edge you can fly to and touch. It's a boundary in time, a horizon of causality beyond which no signal has had the time to arrive. In other words, the limit is not in space, it's in your experience of it. Every time you look at the night sky, you're seeing light that left its source billions of years ago, and you're looking deeper into the past with every step outward. But there's a point beyond which the light hasn't had enough time to get here, even though the universe itself might keep going. This creates a strange situation. The universe may be infinite, but your view of it is not. It's like standing inside a giant sphere of fog that clears only as fast as light can travel. And no matter how hard you try, you can never look beyond that sphere. But this fog isn't static. It changes with time. As the universe gets older, light from farther distances gets a chance to reach us, and so our observable universe slowly expands. But even this expansion has its limits. Because of the accelerating expansion of space, driven by something we call dark energy, some regions are moving away from us so quickly that their light will never, ever reach us, not even if we wait forever. That means that although we think of the observable universe as growing, it's actually shrinking in terms of what we can eventually access. Some parts that are visible now won't be visible in the far future, and others will never be visible at all. And yet, they exist. There could be countless galaxies out there, stars, planets, maybe even civilizations, all forever cut off from our view. Not because they're behind a wall, but because the distance is too vast and the expansion too fast. This is why the phrase, edge of the universe, is misleading. It makes you think of a border or a cliff, like the edge of a table or the rim of a bowl. But the universe doesn't work like that. It's not a place you can point to and say, here it ends. It's more like an idea that only makes sense inside the rules of light and observation. The real edge, if you want to call it that, is the edge of what we can ever know, not what exists. It's the boundary of possible experience, not of actual being. And this has deep implications. It means that when we study the universe, when we make maps and take pictures and write equations, we're really studying just one little part of a much larger story, a story whose other chapters we'll never get to read. But that doesn't make them less real. Just because you can't see something doesn't mean it isn't there. And just because we are limited doesn't mean the universe is. Our bubble of vision is not the universe's prison. It's our own. So the next time someone asks where the universe ends, you can tell them it doesn't. It keeps going, possibly forever, in directions we can't point to, beyond distances we can't travel, filled with wonders we can't imagine. And the only thing stopping us from seeing it is the clock on the wall and the laws of physics that keep the speed of light constant. You are standing at the center of your own cosmic horizon, surrounded by a glowing shell of ancient starlight. And beyond that shell lies a realm of mystery, dark, silent, unreachable, but just as real as the stars above your head. And knowing that should not make you feel small. It should make you feel lucky, because you are here, in a universe without edges, with eyes that can see billions of light. Years in a moment when light is still arriving from places that soon will vanish from view forever. You live on the edge, not of space, but of perception. And every star you see is a gift from the cosmos, a reminder that there is always more than meets the eye. The balloon analogy, a 2D surface expanding in higher dimensions. You might think the universe is stretching like a giant explosion into empty space, with galaxies flying outward into some vast black nothingness. But what if that picture is misleading, and the real story is not about things moving through space, but space itself growing in a way we can't fully imagine, not outward into emptiness, but from within, like a surface stretching in more directions than you can see? And to grasp this, scientists often use one of the most powerful and surprisingly simple metaphors in all of cosmology, the balloon analogy, where instead of trying to picture our three-dimensional universe expanding into a fourth spatial dimension we can't perceive, you imagine a two-dimensional world living on the surface of a balloon, where everything those creatures can see and measure exists only on that surface. And as the balloon inflates, their universe expands, not because they are moving through space, but because space itself is getting bigger between every point. Imagine you're a tiny ant stuck to the surface of a balloon, and your whole world is that surface. You can go left and right, forward and back, but you cannot go up or down the way someone outside the balloon can to you. There is no inside or outside, there is only the surface. And yet, as the balloon is blown up, you would notice something strange. Every other ant seems to be getting farther away from you, no matter which direction you look. And the more distant they are, the faster they seem to recede. From your perspective, it might feel like you're at the center of this expansion. But so would every other ant, because the expansion is not happening from a single point. It's happening everywhere at once. And this is exactly what astronomers believe is happening with our universe. We are not watching galaxies speed away through a fixed stage, but watching the stage itself stretch and grow, with space being created between the galaxies, not galaxies flying through space like rockets. The reason this analogy is so helpful is because it lets us separate two very different ideas: moving through space and space itself expanding. And that difference is crucial, because in our universe, it's not that the galaxies are moving away from each other through a static background. It's that the background itself is growing, and that changes everything about how we understand distance, speed, and the limits of observation. But here's where things get more subtle and more fascinating. The balloon's surface to the ants is all there is. They cannot even conceive of the third dimension in which the balloon is inflating. To them, their world is complete, flat from their tiny perspective, and yet curved in a way they can't detect unless they perform very precise measurements. Just like those ants, we live in a three-dimensional universe, and we cannot observe the higher dimensional space, if it even exists, in which our universe might be embedded. We can't step outside our universe to watch it expand. There is no outside as far as we can tell. The balloon analogy doesn't mean the universe is a literal balloon, or that there's something outside pushing it. It's a way of understanding how space can expand without needing an edge or a center. In the same way the balloon's surface has no edge, our universe might be infinite, or closed on itself in a higher dimensional way, and the expansion is not pushing into anything. It's simply stretching what already exists. This leads to strange but real consequences. For example, if you were to shine a flashlight across the balloon's surface, the light would travel along that curved path, and if the balloon was big enough and light fast enough, it might eventually return to you from the opposite direction, like a message that traveled the long way around. In theory, the same could be true of our universe, if it were closed in a higher dimension. Light could loop back after billions of years, showing us a copy of something we thought was far away, but we don't currently see signs of such looping, which might suggest the universe is flat or open and infinite, though our ability to measure curvature on cosmic scales is limited by what we can observe. Still, the balloon analogy helps us think in ways that escape the prison of ordinary experience. It helps us grasp how the Big Bang wasn't an explosion at a point, but an expansion of all space, from an earlier, hotter, denser state. There was no center, no edge, no direction from which the universe burst forth. Every point in space, including the one where you're sitting right now, was once part of that early fireball, and every point is still participating in the ongoing stretching of space. like dots on the surface of a growing balloon. But unlike a balloon, the universe doesn't require a surrounding space to grow into. It creates more space from within. That's the part most people struggle to accept. In daily life, you can't picture something getting bigger without it pushing into somewhere else. But in general relativity, the geometry of space itself can evolve. It's like drawing a square on a rubber sheet and watching the square grow as you stretch the sheet. The square doesn't move. The space around it changes. And just like the ants on the balloon, we can measure that change not by seeing space stretch directly, but by seeing how distant galaxies appear to recede, and how the light from them becomes redshifted, stretched out by the same expansion that separates us. That redshift is like the fingerprint of expansion. The farther away a galaxy is, the more its light is shifted toward the red end of the spectrum, not because it's speeding away through space, but because the space between us and it has stretched during the time the light was traveling. This is how we know the universe is expanding. It's not just a theory, it's something we observe in the data, and the balloon analogy helps us wrap our minds around it. But even this analogy has limits. For one, the balloon has an inside and outside, while our universe may not. The balloon analogy is a shadow of a deeper truth, a tool to stretch our imagination closer to the nature of space and time. And it opens the door to an even deeper question. What is space made of? And how can it grow? Is it a real thing, like a fabric that can bend and stretch? Or is it just a mathematical backdrop, a way to describe how matter and energy behave? Einstein's theory suggests space is dynamic. It can curve, ripple, and expand. But quantum physics hints that at the smallest scales, space might not be smooth at all. It might be grainy, foamy, or even made of information. And if space itself is emergent, like a pattern that comes from deeper rules, then the expansion of space might be more like the unfolding of a computation than the stretching of a substance. The balloon analogy helps us step toward that understanding, but it also reminds us of our limits. We are like those ants, drawing lines and symbols on a surface we cannot fully grasp, trying to make sense of a universe that expands in ways we can only model, not truly picture. Yet, even in our smallness, we've built tools, telescopes, and theories that let us glimpse how it all fits together. And that's the beauty of science. It turns metaphors into measurements and dreams into data. So the next time you see a balloon rising into the air, think of the universe, not as a thing expanding into something else, but as space itself growing from within, carrying galaxies farther apart, not by pushing them through space, but by creating more space between them, with no edge, no center, and no outside. Just a vast, unfolding surface of possibilities, wrapped in laws we're still just beginning to understand. There's no absolute position in the cosmos, only relations. You might believe there's such a thing as a fixed place in the universe, a cosmic address where something simply is, no matter what else is moving. But what if the truth is far more puzzling and beautiful than that? And what we call position is not a property that belongs to anything by itself, but something that only makes sense when compared to something else, like a dance step that means nothing. If there's no partner, in other words, there's no absolute location in the cosmos, only relationships between things. And this idea, strange as it sounds, is not just philosophy. It's at the heart of physics itself, shaping how we understand motion, gravity, time, and even the very structure of space. To grasp this, you need to forget the way we think about places in daily life, where your room is above the ground, the tree is next to the house, the moon is up in the sky, and the stars are way out beyond. But those are all descriptions made from comparisons, from a viewpoint, and if you take away the reference, the meaning disappears. Where is the moon? Exactly, if you don't say where it is relative to Earth. Where is Earth if you don't measure it from the Sunday? And where is the Sunday if you don't place it within the galaxy? The farther you zoom out, the clearer it becomes that position is never absolute. It is always part of a relationship. And this realization reaches its full power in Einstein's theory of relativity, which says not only is position relative, but so is time and motion itself. Imagine two spaceships floating in deep space, far from stars and planets, and each one sees the other moving. Who is really in motion? The answer is that both answers are equally valid. Motion only exists as a comparison. There's no invisible grid out there marking who's standing still and who's speeding by. And this isn't just a clever thought experiment, it's how nature works. Even light, which travels at a constant speed in every direction, does not define a fixed reference point. No matter how fast you are moving, you always measure light to be traveling at the same speed. And this breaks the idea of an absolute frame of rest. There's no master clock ticking at the center of the cosmos. No special spot where space and time are anchored. Everything is moving, and yet nothing is the center. This brings us to a profound shift in perspective. You can never describe where you are in the universe without saying where you are in relation to something else. Even the coordinates astronomers use to map the stars are based on reference points, like Earth's equator, or the orientation of distant galaxies. Remove those, and there's no map left, only a sea of relations, and it goes deeper. Quantum physics, the science of the tiniest things, tells us that particles don't even have definite positions until they're measured. Their location is a cloud of probabilities. And what collapses that cloud into a specific spot is not some hidden property, but an interaction, a relation. It's as if the universe only draws a dot on the page when something else is there to point at it. Without that, the dot remains a blur. The same is true of gravity. In Einstein's view, gravity is not a force pulling things from a fixed place in space. It's the bending of space itself, caused by the presence of mass and energy, and how that bending affects the paths of nearby objects. So again, the behavior of one thing depends on the presence of another. Even time ticks differently, depending on your speed and gravity. A clock on a mountaintop ticks slightly faster than one at sea level. Time itself is not absolute. It too is a relation. And that means your very sense of when and where is shaped by the invisible dance between you and everything else. If you were the only thing in the universe, there would be no motion, no time, no location. Because those ideas depend on comparison, if everything was the same everywhere, there would be no way to say what moved or where. Reality, then, is a web of relations, and position is not a label pinned to objects, but a description of how things are connected. This is one of the most humbling and powerful lessons in science. It tells us that our place in the cosmos is not fixed, not anchored to any divine grid or cosmic center. We float, like everything else, in a sea of changing distances, where the meaning of location is always built from context. You might ask then, if everything is relative, how do we do anything? How do we navigate, build, explore? The answer is, we build local frames. GPS works not by finding your location in some absolute sense, but by comparing the timing of signals from multiple satellites. The coordinates it gives you are based on Earth's surface and the rotation of the planet, again all relative. Astronomers locate galaxies by comparing redshifts and angles, not by referencing a universal map. Even the concept of here is meaningless without a there. This has philosophical consequences too. It tells you that nothing exists in isolation. To be anywhere is to be in relation. To matter is to be part of a pattern. And this is not just metaphor, it's physics. The equations that describe the universe are built from differences, not absolutes. They describe how one thing changes compared to another, not how it behaves in isolation. When you look at the night sky and imagine stars fixed in place, remember that they too are moving, not through a background stage, but as part of a vast interconnected ballet where no one has a throne and no one has a starting line. Even the center of the universe is a misleading idea. There's no privileged spot. Every point is as valid as any other. You are not at the edge, nor are you in the middle. You are somewhere, and that somewhere is only meaningful because there are other things to compare it to. That's what gives structure to space and rhythm to time. Without relation, there is no cosmos. And so when you ask, where are we in the universe? The most truthful answer is, we are where everything else is not. Your place is a contrast, not a location. And this teaches you to see not just the stars, but the connections between them. Not just the points, but the lines. In the end, physics whispers something deep and quiet to those who listen closely, that the universe does not care for absolutes. It sings in patterns, dances in comparisons, and builds its beauty from the simple truth that nothing is anything by itself. Everything is what it is in relation to something else. And you, your body, your mind, your presence, are part of that great web, not a dot on a map, but a thread in the fabric. The universe might be infinite or curve back on itself. You might imagine the universe as something that has a size, a shape, a beginning point, and maybe even an edge somewhere out there in the darkness. But what if the universe is playing a deeper trick, hiding something far more astonishing than distance? And the truth is that the cosmos might stretch on forever without ever ending, or even more strangely, it might be infinite in a different way, not by going on forever in a straight line, but by curving back on itself so perfectly that if you traveled far enough in one direction, you could eventually end up where you started. Just like how walking in a straight line on the surface of Earth will eventually bring you full circle. This might sound like science fiction, but it's a real serious question in modern physics, one that has fascinated astronomers and philosophers for centuries, because it forces us to rethink the very idea of what a universe is. Whether it's a boundless ocean of space stretching out without limit, or a kind of cosmic loop that has no edge yet, is still somehow finite. Like the surface of a sphere in 3 dimensions, or the skin of a balloon in a higher one. To understand this, you have to let go of some everyday assumptions in our normal lives. Most things we interact with have clear boundaries. A room has walls, a road has a beginning and an end, a paper has edges. But when it comes to the universe, these rules break down. Space is not like an object sitting in a bigger container. It is the container, and it might not be sitting in anything. The universe might not be expanding into something else, but simply expanding from within, and that makes it incredibly hard to picture. So scientists rely on mathematics and observation to find clues about the universe's shape. They ask questions like, does space go on forever, or does it wrap around in some complex way? Is the total amount of space infinite, or is it just very, very big, but still looped? To investigate this, astronomers look for signs of curvature. Just like you can tell, you're on a curved surface by measuring angles and distances. Say in a triangle drawn on a ball versus one on a flat table. You can do the same with light and matter in the cosmos. If the universe is positively curved, like a sphere, then parallel lines will eventually meet. If it's negatively curved, like a saddle, parallel lines will diverge. And if it's flat, they stay the same distance apart forever. Surprisingly, all the evidence we have so far suggests the universe is flat, or at least so close to flat, that we can't yet detect any curvature, even when looking across billions of light years. But here's the catch. Flatness does not automatically mean infinity. A flat universe could still be finite if it loops back on itself in a certain way, like a video game world, where going off one edge of the screen brings you back on the other side. This kind of topology is hard to picture in 3 dimensions but perfectly possible in math. It means the universe could be like a torus, a donut shape, or something even more exotic, like a higher dimensional analog, where directions curve around invisibly. In such a universe, if you had an unimaginably powerful telescope, you might even see the back of your own head, not because you turned around, but because the light from your body could loop all the way around space and come back from behind you. We haven't seen that, but the idea isn't ruled out yet. Meanwhile, the concept of an infinite universe raises different mysteries. If the cosmos truly goes on forever in all directions, then it would contain not just countless galaxies and stars, but possibly infinite repetitions of matter, patterns, and even you in an infinite universe. Every possible arrangement of particles must exist somewhere, just by chance. That means there could be another Earth, another solar system, even another version of you reading these words right now, just unimaginably far away. Not because of magic, but because of pure probability. This kind of infinity is overwhelming to think about. Our brains are not built to grasp the meaning of endlessness. We can count higher and higher, imagine bigger and bigger spaces, but we can't really feel what it's like to exist in something without limits. And yet, nature may not care about our limits of imagination. The observable universe, the part we can see, is huge but not infinite. It stretches about 93 billion light-years across, because that's how far light has had time to travel since the Big Bang. But beyond that observable bubble, we don't know what lies. It could be more galaxies, more stars, more space, just like ours. Or it could be the same space, wrapped around. There could be no boundary, no outer edge, no place where you could plant a flag and say, "Here it ends." If you traveled far enough in a straight line, you might come back to where you began, without ever finding a wall or border. This idea, that the universe is finite but unbounded, is one of the most profound concepts in science. It challenges the way we think about beginning and end, about here and there. It means the cosmos could be self-contained, like the surface of a planet, but in 3 dimensions instead of 2. And just like Earth's surface doesn't have an edge you can fall off, space itself might not either. But how could we ever know for sure? That's the hard part. We can only observe a tiny patch of the total universe, limited by the speed of light and the age of time. We are like fish in a vast ocean, trying to guess the shape of the sea from the waves that reach our reef. We measure background radiation, map the distribution of galaxies, study the bending of light across space, all to look for clues about curvature and topology. And the more we look, the more it seems the universe is either truly infinite or unimaginably vast and curved so gently that it looks flat to us. Either way, it leaves us with wonder. Because if the universe is infinite, then the possibilities are too. There is no end to how far you can go, how much you can learn, or how many versions of reality might exist. If it is finite and curved, then we live in a cosmic hall of mirrors, where space and time twist in elegant loops, and the universe contains itself, like a puzzle with no outside. Both ideas are equally humbling, because in neither case are we at the center. We are not at the edge, nor are we special. We are simply part of a much larger story, one that might never be fully visible to us. And yet, here we are, thinking about it, wondering, measuring, dreaming. That perhaps is the most beautiful part. The universe might go on forever, or it might wrap around like a cosmic sphere. But either way, it has given rise to minds that can ask the question. It has folded into itself the possibility of curiosity, of exploration, of awe. And so when you look up at the stars, remember that what you see is only a small piece of a much larger reality, one that may never end, or may end only by returning to its beginning. Either way, you are not separate from it. You are inside it, and whether the universe is infinite or curved, whether it stretches forever or loops back on itself, it is not just a place where you live, it is a living part of you. Curved space can be finite, but boundless. You might believe that for something to be finite, it must have an edge, a boundary, a stopping point where everything comes to a halt. But what if that idea, so intuitive in daily life, collapses completely when we talk about the universe? And the truth is that space can be both finite and yet boundless at the same time, like a road that never ends, even though it covers only a limited area, or a surface you could travel forever, without ever falling off or hitting a wall. Because in the strange geometry of our cosmos, space itself can be curved in such a way that it loops endlessly without requiring any outside or border at all. And this isn't just a poetic image, it's one of the most mind-opening and mathematically accurate ways to describe what space might actually be. To really understand this idea, you have to leave behind the way you experience shapes and sizes in your ordinary world, where rooms have walls, books have covers, and boxes have corners. In your daily life, everything you know is surrounded by something else. If you see a playground, it ends where the fence is. If you draw a square, its lines contain it. So your mind naturally assumes that everything that is finite must be enclosed. But nature doesn't always follow our instincts. In geometry, there are shapes that are limited in size but have no edges. The simplest example is the surface of a sphere. Imagine a bug crawling along the skin of a basketball. From the bug's point of view, it could keep crawling forever, in any direction, without ever reaching a wall or cliff. There's no end to the surface, yet the total area is definitely limited. The bug would eventually return to where it started. That's what we mean by finite but unbounded. And now, take that idea and expand it into 3 dimensions. Imagine space itself, not just as a flat, empty volume, but as something that curves around itself in ways that we inside it might not be able to perceive directly. You wouldn't notice the curve of space by simply looking around. Just like the bug on the basketball thinks it's walking on a flat field, we might think our universe is flat, even if it isn't, because the curvature only reveals itself through careful measurement, not everyday experience. The reason this matters is because it changes how we think about the structure of the universe. We often ask questions like, where does the universe end? Or, what's outside the universe? But in a curved, finite, boundless space, those questions lose meaning. There is no outside. There is no edge. Space doesn't need to be infinite to be endless. It only needs to be curved in the right way. This was one of the key insights from Albert Einstein's theory of general relativity, which showed that massive objects can bend the space around them. And if you apply this idea to the whole universe, it becomes possible for space to curve on itself, not in a way we can step back and see, because we are inside it, but in a way that shows up in how galaxies move, how light travels, and how the universe expands. Imagine traveling in a straight line through space, at incredible speeds, for billions of years. In a curved, boundless universe, you would never reach an edge. You might, however, come back to your starting point from the other side, without ever turning. That's the essence of unboundedness. And this isn't just theoretical. Scientists have actually tried to detect signs of such curvature by looking at the cosmic microwave background, the faint glow left over from the Big Bang. They look for repeated patterns in the sky, circles that match in temperature and shape, as if the light had wrapped around the universe and come back from different directions. So far, we haven't seen clear evidence of such a loop, but the measurements are very close to what we'd expect in a flat or slightly curved space. The margins are small, which means the universe could still be gently curved in a way we can't detect yet. Even more fascinating is the fact that if the universe is positively curved, like the surface of a sphere, then it must be finite in volume. But because there's no edge, it's boundless. It's like living on the surface of Earth. No matter how far you travel, you never fall off. The horizon just keeps opening in front of you, but the total surface area is still limited. The same could be true for space itself, and that leads to deep, humbling questions. If the universe is finite but boundless, how big is it? How many galaxies, stars, and planets fit into this cosmic curve? Is our observable universe just one tiny patch of a larger folded reality? And if we could somehow map the entire curvature, would we find that our universe is a closed shape that contains all of space and time within itself, needing nothing outside it to exist? That's what makes this idea so powerful. It doesn't just describe a possible shape, it redefines our understanding of existence. We tend to think that things need something else to contain them, that boxes need rooms, rooms need buildings, buildings need ground. But if space is curved and self-contained, it needs nothing beyond it. It simply is. It contains itself. And that flips our perspective. We are not sitting inside a big container called the universe. We are woven into the fabric of it, our atoms, our thoughts, our history, all part of the curved geometry that stretches and loops and folds, perhaps infinitely, perhaps not, but always without an edge. And this has consequences not just for maps, but for meaning. Because in a universe without boundaries, there are no privileged positions, no centers, no front or back. Everywhere is just as valid as anywhere else. And that includes you. You are not on the edge of anything. You are not on a path towards some wall. You are inside a space that may go on forever, or may wrap perfectly, quietly around itself. And either way, you belong to it completely. So the next time you look up at the stars and wonder where it all ends, remember this: it might not end at all. Not because it stretches forever, but because it folds without breaking, curves without stopping, surrounds without surrounding anything. And the miracle is, even in that vast, boundless curve, even in a universe without edges or outsides, you are here, thinking, asking, feeling, alive within the shape of everything. Expansion can outpace the speed of light. And that's okay. You might think that nothing in the universe can ever move faster than light, that the speed of light is the ultimate cosmic speed limit, and that if something tried to go faster, the laws of physics would step in and stop it. But what if that idea, while true for objects moving through space, doesn't apply to space itself? And what if the universe has found a clever loophole, not by breaking the rules, but by bending the very playing field, so that the fabric of space can stretch faster than light, without violating any physical law? And this strange truth is not just a theoretical curiosity. It's one of the most profound and misunderstood aspects of modern cosmology, because it means that distant galaxies are not flying through space at impossible speeds. They are being carried away by the growth of space itself, like ants sitting on a balloon that's being inflated faster than they can crawl. And understanding this distinction changes everything about how we view the universe, the limits of observation, and even the ultimate fate of everything we know. To make sense of this, we need to separate two things that sound similar, but are fundamentally different: motion through space and the expansion of space. When Einstein developed the theory of special relativity, he showed that nothing with mass can move through space faster than light. That rule still holds. You can't build a spaceship that outruns a photon. But Einstein's later theory, general relativity, introduced a different idea. Space is not a rigid, unchanging stage. It can curve, ripple, and stretch. And when space itself expands, it is not carrying things through space. It is making more space between things. This subtle but critical difference is what allows cosmic expansion to outpace light without breaking the speed limit, because nothing is moving faster than light locally. Instead, the distances themselves are growing. Imagine two dots drawn on a stretchy piece of rubber. If you stretch the rubber slowly, the dots move apart, gradually, but if you stretch it fast enough, they can end up separating faster than any signal could travel between them. That's what's happening on a cosmic scale. Galaxies are not breaking the light barrier. The space between them is growing so rapidly that the total separation increases faster than light could cross it. And this isn't just speculation. It's something we observe. Distant galaxies appear to be receding from us at speeds faster than light. This doesn't mean they are speeding through space. It means the expanding space between us is growing faster than light can traverse. This is why, when we look out far enough, we see a limit, the cosmological horizon, beyond which light from those regions will never reach us, no matter how long we wait. They are not invisible because they are too dim or too far, but because the space between us is expanding too quickly. It's like trying to swim across a river that's widening faster than you can swim. No matter how hard you try, the opposite shore keeps retreating. And this brings up a strange but real idea. There are parts of the universe that are already permanently out of reach. Not because of distance alone, but because of how space itself behaves. Every second that passes, more of the universe slips beyond this horizon. Light emitted from those places today will never arrive. We will never know what is happening there. Not because we lack the technology, but because of the very nature of space and time. This leads to a common question. If space can expand faster than light, does this mean we could use it to travel faster than light? Could we build a spaceship that rides this expansion to reach distant galaxies instantly? In theory, concepts like wormholes or warp drives try to use this principle, manipulating the geometry of space rather than moving through it. But these remain hypothetical, requiring exotic conditions or unknown forms of energy. What is certain, though, is that the universe itself uses this trick all the time. During the earliest moments of the cosmos, a period called cosmic inflation, space expanded unimaginably fast, many times faster than the speed of light, stretching tiny quantum fluctuations into the vast structures we see today. That rapid expansion did not involve anything moving faster than light locally. It involved the space itself ballooning at extraordinary rates. And because of that, regions that were once in contact became causally disconnected, separated forever by the swelling fabric of space. Today, the universe continues to expand, though at a much slower rate, but due to dark energy, this expansion is accelerating. That means more and more of the universe will cross the horizon of observability, not because it is disappearing, but because the space between us is growing faster than light can overcome. This paints a haunting picture of the far future. In trillions of years, the galaxies we now see will fade from view, leaving future observers in isolated pockets of space, unable to detect the grand cosmic web that once connected them to everything else. They might look into the sky and see only darkness, unaware that they are part of something much larger. And yet, this outcome is not due to speed in the conventional sense. It is due to expansion. It is the difference between running and being on a conveyor belt that's speeding up beneath your feet. No law is being broken. Instead, the rules of space itself are being obeyed in ways that seem almost magical. So how do we know this is true? We see it in the redshift of galaxies, the way their light stretches as it travels to us. The farther a galaxy is, the more its light is shifted toward the red end of the spectrum, because the space it passed through has expanded during its journey. We measure this redshift carefully, and it tells us not just how fast galaxies are moving away, but how space itself is changing. When astronomers plot this data, they find something extraordinary. Galaxies beyond a certain distance have redshifts so large that their apparent recession speeds exceed the speed of light. And yet, their light still reaches us, if it was emitted long ago before the expansion outpaced light. Light emitted now from those same galaxies will never arrive. They are beyond the point of no return. This teaches us that the observable universe is not the entire universe. It's just the region from which light has had time to reach us. Beyond that lies more space, more galaxies, possibly more structure, but forever invisible. Because expansion can outpace even light. And here's the most mind-bending part, as you sit here reading these words, that boundary is growing. Every second, more of the universe is placed forever beyond your reach, not because it vanishes, but because the space between you and it becomes too fast, too stretched, too far for light to cross. It's not a wall, it's a horizon. A limit imposed not by distance, but by the flow of time and the speed of expansion. And that's okay. It doesn't mean something is wrong with physics. It means physics is deeper than we imagined. The speed of light remains the fastest speed for information and objects within space. But space itself is not bound by that limit. It can grow faster than light, not by breaking laws, but by operating under different ones. This is not a bug in the system. It is a feature of a universe governed by general relativity, a universe where space is not passive, but dynamic. A universe where the rules themselves have layers. And so, the next time you hear someone say that nothing can go faster than light, you can smile and say, that's true, but space can. And in that simple truth lies the key to understanding why we see galaxies fly apart, why the night sky fades with time, and why the universe will one day become a cold, dark, and lonely place. Not because it shrank, but because it expanded too well. That's not a failure of nature. That's the elegance of it. Dark energy pushes space apart, not galaxies away. You might think that when we say the universe is expanding, it's because galaxies are racing away from each other, shooting through space like cosmic fireworks. But what if that picture is completely misleading, and the truth is not that galaxies are moving through space at all, but that space itself is growing between them? And what's more, This growth is not being powered by the leftover energy of the Big Bang, but by something far stranger, something we don't fully understand yet, something we call dark energy, a force not of explosion, but of expansion, not of movement, but of making more space, silently and invisibly increasing the distance between things without pushing on the galaxies themselves, like a gust of wind or an invisible hand. And understanding this subtle but critical distinction changes the entire way we think about the universe and our place in it. Imagine two dots drawn on the surface of a balloon. As the balloon inflates, the dots get farther apart, not because they're crawling away from each other, but because the surface between them is stretching. If you lived on that surface, you might think the dots are moving, but they are not. The space itself is expanding. This is the key to understanding the role of dark energy. It's not a repulsive force pushing galaxies outward like billiard balls, but a property of space itself, causing space to expand more and more as time goes on. To see how strange this is, consider this. If you remove all the galaxies, all the matter, and all the radiation from the universe, leaving behind pure emptiness, you might expect nothing to happen. But that's not what the equations of general relativity say. They tell us that even in a perfect vacuum, space can still expand if dark energy is present, because dark energy doesn't depend on matter to act. It is woven into the fabric of space, and its effect is not to push on objects, but to change the geometry of the universe itself. This is why galaxies don't feel a wind or force pulling them apart. If you were to sit inside a galaxy, you wouldn't notice anything stretching or tugging. Local space, like the space inside galaxies or solar systems, remains gravitationally bound. What changes is the space between clusters of galaxies, where gravity is weaker. That space stretches, not by pushing the galaxies outward, but by adding more distance between them at every moment. This is also why galaxies farther away appear to recede faster, not because they're moving faster through space, but because there's more space between us and them being expanded. And the farther the light has to travel, the more expansion it experiences along the way. Which is why we see a redshift in distant galaxies. Their light has been stretched, not by motion through space, but by the stretching of space itself. This phenomenon is not something we guessed. It is something we measure. The light from faraway galaxies carries with it a record of how the universe has changed over time. By studying that light, scientists discovered something shocking in the late 1990s. The expansion of the universe is not slowing down. As everyone expected, it's speeding up. That discovery led to the idea of dark energy, a term we use to describe whatever is causing this accelerated expansion. But the name is misleading. It is not energy in the usual sense. We don't know what it's made of, or even if it is a substance at all. It could be a property of the vacuum. It could be an effect of a quantum field, or it could be something even stranger, something that lies beyond our current theories. What we do know is this: about 68% of the total energy content of the universe is dark energy. That means the dominant force shaping the cosmos today is something we don't understand. It's not matter, it's not light, it's not dark matter, and it is acting everywhere, evenly, constantly across all of space. Not by pushing, but by changing the rules of geometry. It causes the scale of the universe to grow. And the more the universe grows, the more dark energy there is, because dark energy is tied to space itself. So as space expands, there's more room for dark energy to exist. And that causes even more expansion, in a feedback loop that never slows down. This is why scientists believe the universe's future is not a big crunch, but a big freeze. Over time, galaxies will move beyond our cosmic horizon. Stars will burn out, matter will decay, and space will continue to expand. Not because something is pushing it, but because space itself wants to grow. This paints a picture of a universe that is not being driven outward by explosions, but one that is quietly and relentlessly stretching, driven by an invisible presence that doesn't act on objects, but on emptiness itself. That's the essence of dark energy, and it raises deep questions. What is the nature of this energy? Is it truly constant, or does it evolve with time? Could it reverse? Could it change the fate of the cosmos? Some theories suggest dark energy might eventually become unstable, triggering a collapse or a transformation. Others suggest it might increase over time, leading to a big rip scenario, where even atoms are torn apart as space expands faster than any force can resist. But those are only possibilities. For now, all we know is that space expands not because galaxies are being pushed, but because space is being stretched. And this leads to one of the most important lessons in modern cosmology. Movement is not the only way distances can grow. Expansion is not always about things changing position. Sometimes, it's the coordinate system itself that changes. This is why you can have galaxies moving away from each other faster than the speed of light. Not because they're breaking a law, but because space is expanding faster than light can travel. And because dark energy affects all space, it doesn't need to push on anything to cause this. Its influence is not mechanical, but geometric. It changes the shape of the universe silently, steadily, and without resistance. That's why dark energy is so difficult to detect directly. It doesn't clump, it doesn't radiate, it doesn't pull, it simply expands. And yet, this invisible actor now dominates the destiny of everything. So when you hear that the universe is expanding faster and faster, don't picture galaxies fleeing like frightened animals. Picture space itself growing like a canvas being stretched. Not because something is pulling at the edges, but because the fabric itself is changing in size, driven by a force that operates not on things, but on the nothing between them. That is what dark energy does. It doesn't push galaxies. It grows the space that holds them. And that quiet difference explains the future of everything. The expansion of the universe is accelerating, not slowing. You might expect that after billions of years of cosmic expansion, the universe would be gradually running out of steam, that the initial energy from the Big Bang would eventually fade. Gravity would begin to pull everything back together, and the growth of space would slow down like a stone tossed into the air, finally giving in to gravity. But what if that assumption is not only wrong, but the opposite of what's really happening? And the truth is that the expansion of the universe is not decelerating, but accelerating, growing faster and faster, with time as if some hidden engine is continuously adding fuel to the cosmic fire. Not through explosions or collisions, but by silently stretching the very fabric of space itself. And what's even more unsettling is that this unexpected acceleration is not a future prediction. It is already happening right now, all around us, and we only discovered it by accident. By peering deep into the cosmos and noticing that the light from distant stars was telling a story very different from what we had imagined, a story that defied gravity, rewrote our equations, and introduced a force we still don't understand, known simply as dark energy, which seems to be driving this expansion not just forward, but faster. For most of the 20th century, cosmologists believed that the universe's expansion, which began with the Big Bang, would be gradually slowing down under the pull of gravity, the mutual attraction of all the matter in the universe, pulling back against the initial outward push, like the brakes on a car slowly bringing it to a stop. The only question seemed to be whether the universe had enough mass to eventually reverse the expansion and collapse back in a big crunch, or whether it would keep expanding forever, but at an ever-decreasing rate, like a ball tossed upward that never quite falls back, but slows more and more over time. Nobody seriously expected that the expansion might actually be speeding up. It wasn't until the late 1990s, when two teams of astronomers studied the light from exploding stars called Type ER supernovae, that the shocking truth began to emerge. These stellar explosions act as standard candles because they all shine with roughly the same intrinsic brightness, allowing astronomers to calculate how far away they are based on how dim they appear. When they compared this distance with how fast the galaxies hosting these supernovae were receding, they expected to find signs of slowing expansion. Instead, the supernovae appeared dimmer than expected, as if the galaxies were farther away than they should be in a decelerating universe. This meant only one thing: the expansion was not slowing down, it was speeding up. The discovery was so startling, so contrary to intuition and theory, that it won the 2011 Nobel Prize in Physics. And with that discovery came a flood of new questions. What could be causing this acceleration? Where was the extra energy coming from? Why now and not earlier or later? The simplest explanation, and still the best, fitting one today, is that space is filled with a form of energy that does not dilute as the universe expands, unlike matter and radiation. This energy, dubbed dark energy, is believed to have a constant density, meaning that as more space is created, more dark energy fills it, keeping the total density the same but increasing its influence as the universe grows. Because dark energy doesn't clump or weaken with time, it dominates more and more of the cosmic budget as the universe ages. In the early universe, matter and radiation were dense and powerful, and their gravity slowed expansion. But as space expanded, the density of matter decreased, while dark energy's density remained constant, eventually taking over as the dominant force. This transition is believed to have happened a few billion years ago, and since then, the expansion has been accelerating. Today, dark energy accounts for about 68% of the total energy in the universe. Matter, including all the galaxies, stars, gas, dust, and even dark matter, makes up only about 32%. This means that the structure and fate of the entire cosmos is now being dictated by something we cannot see, cannot touch, and do not yet understand. And its effect is not just distant. It affects everything, everywhere, including the future. As the universe accelerates, galaxies move away from each other faster and faster. Over time, the rate of separation increases, and the observable universe, already limited by the speed of light, shrinks in terms of what we can ever reach. More and more of the universe is slipping beyond our cosmic horizon, never to be seen again. In a few trillion years, distant galaxies will vanish from view altogether. Only the local group of galaxies, bound together by gravity, will remain visible. Future civilizations might look out at the sky and see only darkness, unaware that the cosmos once contained trillions of galaxies, now lost to accelerated expansion. This lonely future, known as the cosmic isolation, is not just poetic. It is physically inevitable if the current model holds, and it all stems from the fact that space is not expanding slower, but faster, and this acceleration will continue indefinitely. Even time itself is shaped by this acceleration. In an accelerating universe, cosmic time flows differently than it would in a slowing or stable universe. The timelines of galaxies, stars, and even atoms are subtly stretched by the growth of space. And yet, this acceleration does not come with any violent push or force. It is smooth, silent, relentless. You do not feel it in your body or your surroundings. It is a background shift in the geometry of everything. It acts on the largest scales, shaping the universe, like a potter slowly turning a wheel, invisible but unstoppable. And though we've given it a name, dark energy, that name hides more than it reveals. We don't know if dark energy is a field, a fluid, a property of space, or something else entirely. We don't even know if it's truly constant. It could evolve over time, or even change signs. In some theories, dark energy might one day decay, ending the acceleration and leading to a new cosmic era. In others, it might grow stronger, eventually tearing apart galaxies, stars, planets, and even atoms in a dramatic finale called the Big Rip. But until we have better data or a new theory, the best model we have, the Lambda CDM model, assumes that dark energy is a cosmological constant, a uniform, unchanging energy density pervading all space. And with that assumption, the future is clear. Acceleration will continue. Galaxies will drift apart. Cosmic structures will freeze in place, and the universe will enter a dark, cold, empty phase where entropy rules and light no longer travels between the stars. It is a strange and lonely fate, not of collapse, but of dispersal, not of fire, but of silence. And yet, in this very moment, We live at the perfect time to witness the universe's full story. We can still see the light from galaxies far away, still measure the redshifts that tell us the expansion is speeding up, still map the background radiation from the early universe. We are here at the threshold, in the narrow cosmic window, when both the past and future are visible. And that might be the greatest miracle of all. Because when the universe is accelerating, everything else becomes fleeting. Structures fade, light stretches, time elongates. But knowledge, our ability to understand and reflect, remains. So the next time you wonder what it means to live in a universe that accelerates, remember this. It means you are part of a story that is expanding faster than light. A story powered by a force no one fully understands. A story that will keep going long after the stars have faded and the galaxies have gone. And even if everything else drifts apart, this truth remains. Your moment, right now, is one of the rarest in cosmic history. A moment when you can look out and still see the whole. Black holes store information on their surface, not inside. You might imagine that everything swallowed by a black hole vanishes into a bottomless pit, sinking deeper and deeper into an invisible core where all information is lost forever. But what if the real mystery is not hidden deep inside, but instead etched onto the surface of the black hole itself? And what physicists have slowly come to realize is that the information about everything that falls in may not be stored within the black hole's unreachable depths, but on its boundary, its event horizon, in a way that flips our understanding of volume and space on its head, suggesting that black holes are not just cosmic vacuum cleaners, but also strange holographic vaults where the total information content is determined, not by what's inside but by the size of the outer shell. To grasp why this is such a shocking idea, you have to first understand what a black hole really is. Not just a collapsed star, not just a region of intense gravity, but a place where the known laws of physics are stretched to their breaking point, where the curvature of space becomes infinite, and where light itself cannot escape once it crosses a certain invisible boundary, called the event horizon. For a long time, scientists believed that anything falling into a black hole was gone forever. Its mass would add to the black hole's gravity, but all the details, its shape, structure, composition, only three properties would remain: mass, electric charge, and spin. This idea was summarized in what physicists jokingly call the no-hair theorem, which says that black holes have no distinguishing features. No hair, other than those three numbers. But this led to a profound puzzle. In all other areas of physics, information is conserved. You can smash something to pieces, burn it, or scatter it. But if you know the starting conditions well enough, you can, in principle, reconstruct what it used to be. The equations of quantum mechanics do not allow information to be destroyed. So, if a black hole swallows a book, a planet, or even a person, what happens to the information about the things that went in? If it's lost forever, that would break the fundamental rules of physics. This is known as the black hole information paradox, and for decades, it was one of the biggest unsolved problems in theoretical physics. Then something surprising happened. In the 1970s, Stephen Hawking showed that black holes aren't completely black. Due to quantum effects near the event horizon, black holes emit a faint glow called Hawking radiation. This radiation slowly drains the black hole's mass, meaning that black holes can eventually evaporate and disappear. But if they vanish in the radiation, they release carries no information. Then the information is truly lost, violating the principle of quantum unitarity. The problem got worse. Hawking's original calculations suggested that the radiation is purely thermal. It contains no details about what fell in. So if a black hole evaporates completely, all the information about what it swallowed disappears with it. But then a radical new idea emerged. What if the information isn't lost inside the black hole at all? What if it's stored on the surface, on the event horizon itself? This leads us to one of the most mind-bending principles in modern physics, the holographic principle. The idea is that everything that falls into a black hole is somehow encoded not in the volume inside, but on the two-dimensional surface area of the event horizon. This is like saying that everything happening inside a room is actually encoded on the walls, and that what we think of as a three-dimensional space is really a projection of a two-dimensional surface. This concept was inspired by an earlier insight from physicist Jacob Bekenstein, who proposed that the entropy, a measure of information, of a black hole is proportional to the area of its event horizon, not its volume. This was shocking. In ordinary systems, entropy usually scales with volume, but black holes are different. Their informational content is encoded on a surface. This means that if you double the radius of a black hole, its area, and therefore its entropy, quadruples. The implication is that space inside the black hole is not the place where information lives. It lives on the edge, on the skin. The boundary becomes the brain. Later, string theorists and quantum gravity researchers took this idea further and began exploring how the holographic principle might apply not just to black holes, but to the entire universe. But within the context of black holes, this principle helps resolve the paradox. If the information is somehow smeared across the event horizon, then perhaps Hawking radiation does carry it away, bit by bit, in a subtle way we don't fully understand yet. This could mean that black holes don't destroy information. They scramble it, stretch it, encrypt it onto their surfaces, and slowly release it back into the universe as they evaporate. But what does it mean to say that information is on the surface? We're not talking about ordinary writing or patterns you can touch. This is quantum information, woven into the very fabric of space-time, perhaps in tiny degrees of freedom near the Planck scale. The surface of a black hole might be pixelated at the tiniest level, with each unit of area about the size of a Planck area, holding a bit of information. The mathematics suggests that for every square unit of Planck area on the event horizon, one bit of information can be stored. This gives us a deep connection between geometry and information, between space and knowledge. The black hole becomes not just a gravitational object, but a computer, a processor, a cosmic ledger that records what enters it, even if that record is beyond our ability to read. And the implications go beyond black holes. If information can be encoded on a surface, does that mean space itself is emergent? Is the entire universe a kind of hologram? Are we living inside a three-dimensional projection of a deeper two-dimensional reality? These are open questions, but they begin with black holes. They begin with the realization that the deepest secrets may not be hidden in the depths, but stretched across the surface like shadows on a wall. This also changes how we view the event horizon. It is not just a one-way barrier. It may be a place of intense informational density, where the quantum states of everything that has ever crossed it are entangled and preserved. And if you could somehow decode the surface of a black hole, you might reconstruct what it has eaten. Not perfectly, not easily, but in principle. This also gives new meaning to the death of black holes. As they evaporate, their surfaces shrink, and their information is gradually released into the universe in the form of highly scrambled radiation. From a distance, this radiation looks like heat, but up close, it might carry the ghosts of everything the black hole once contained. And so, the story of a black hole is not a tale of destruction, but of encryption. The core message is this: black holes do not store information in their centers. They store it on their edges, on their surfaces. And this simple reversal, this inside-out logic, is one of the most revolutionary ideas in physics. It tells us that boundaries matter more than volumes, that information clings to horizons, that what you think is hidden might really be encoded where you least expect it. And perhaps the universe itself, vast and deep as it seems, is not a volume filled with stuff, but a boundary filled with code, a surface telling a story, a black hole whispering its secrets from the outside in. The cosmic microwave background is the same in every direction. From wherever you look in the universe, north, south, east, or west, there is something softly glowing, whispering to us from the distant past, a faint bath of microwave light that fills the cosmos evenly, and almost perfectly, no matter where you turn your eyes. And this soft radiation, called the cosmic microwave background, or CMB for short, is not just leftover heat from some ancient event. It is the most important photograph in the history of science. The oldest light we can possibly see, a fossil imprint of the moment the universe became transparent. And its eerie uniformity in every direction is one of the strangest and most powerful clues we have about the nature of reality itself, raising a question that sounds simple but hides deep mystery. Why is this light so incredibly similar across the sky, even between regions that, according to our best understanding, have never had enough time to talk to each other, never had the chance to share information or equalize their temperature, because they are too far apart and the universe is not old enough for light to have traveled between them? And yet, the CMB tells us they are somehow the same, down to the tiniest fractions of a degree. To appreciate how bizarre and beautiful this is, imagine heating a room with two heaters placed on opposite ends, with no airflow or mixing between them. And yet, after just a moment, the entire room reaches exactly the same temperature everywhere. Such a thing would be impossible without communication. And yet, in the case of the cosmic microwave background, that's exactly what we observe. This background radiation was released roughly years after the Big Bang, when the universe had cooled enough for atoms to form and photons. The particles of light could travel freely without constantly scattering off electrons, which had until then trapped them in an opaque soup of plasma. When this transition happened, light decoupled from matter and began its long journey through the universe, stretching into microwaves as space expanded over the next billion years. What makes this light extraordinary is not just its age, but its perfection. We detect it as a nearly uniform glow at a temperature of about Kelvin above absolute zero, the same no matter which direction we point our instruments. This uniformity is not only impressive, it is puzzling. According to classical models of cosmology, there simply should not have been enough time for all parts of the early universe to come to the same temperature, because information, including heat and light, can travel no faster than the speed of light. So how did the entire observable universe reach such thermal equilibrium so early? This is known as the horizon problem, and it remained unsolved for years. A cosmic inconsistency between observation and theory. Then came a revolutionary idea called inflation. In the early phase, physicist Alan Guth and others proposed that in the first tiny fraction of a second after the Big Bang, far less than a blink, perhaps just a trillionth of a second, the universe underwent a period of rapid exponential expansion, blowing up in size by an unimaginable factor in almost no time at all. This expansion stretched tiny uniform regions of space to cosmic scales, making areas that were once in thermal contact appear far apart today, even though they were once close enough to exchange heat and information. In this way, inflation explains why the cosmic microwave background is so uniform across the sky, because the regions we now see as disconnected were once part of a single smooth patch of space. The smoothness of the CMB is a kind of echo of that shared beginning. But the story doesn't end there. While the CMB is incredibly uniform, it is not perfectly so. Tiny fluctuations, just 1 part in 100,000, ripple across the sky. These minute differences in temperature are not noise. They are the seeds of all the structure in the universe today. Where the CMB was slightly hotter or denser, gravity pulled more matter together, leading to the formation of galaxies, stars, and planets. In other words, the very reason you exist, the reason Earth exists, is because the early universe was not perfectly smooth. And yet, the underlying smoothness is still striking. This balancing act between sameness and variation tells us something profound about the initial conditions of the universe and the laws that govern it. Every time we map the CMB in greater detail, observations from satellites like COBE, NAP and Planck have confirmed the predictions of the inflationary model with exquisite precision, and they've revealed the age composition and geometry of the universe with remarkable accuracy. From these measurements, we've learned that the universe is flat, that ordinary matter makes up less than 5% of its content, and that dark matter and dark energy dominate the rest. But perhaps most importantly, the CMB tells us that the universe was born not in chaos, but in harmony. Its earliest light spread evenly across all directions, like a message written into the structure of space itself. Still, even with inflation, some questions remain. What exactly triggered inflation? What caused it to stop? Is the inflationary field connected to known particles, or is it something completely new? And could the fluctuations in the CMB carry traces of deeper physics, perhaps from the unification of forces, or even the quantum nature of gravity? These questions keep physicists awake at night, because the answers may reshape everything we know. Moreover, the uniformity of the CMB raises philosophical questions. If the universe looks the same in every direction, does that mean there is no center, no preferred location? According to the cosmological principle, yes, the universe is homogeneous and isotropic on large scales, meaning no point or direction is special. This reinforces the idea that we are not in a privileged spot in the cosmos. No matter where you are, the CMB would look the same. In a sense, it is the ultimate equalizer, reminding us that all observers, everywhere, share the same cosmic origin, and yet, tiny differences in the CMB, such as the dipole anisotropy caused by our motion through space, also tell us our place within this vast web. We are moving relative to the CMB, and this motion gives us a frame of reference to measure velocities of other galaxies. So even the uniform background becomes a cosmic compass. Furthermore, the polarization of the CMB, subtle patterns in the direction of the light waves, offers yet another window into the early universe. These patterns are influenced by gravitational waves from inflation, and detecting them could provide direct evidence for the violent stretching of space in those first fractions of a second. Teams around the world are building ever more sensitive instruments to hunt for this signature, if found. It would not just confirm inflation, it would open a new era in cosmology, letting us peer further back than the CMB itself, into the first instance of time. But even without those discoveries, the fact remains that the CMB surrounds us like a shell of memory, a frozen moment from when the universe took its first breath of transparency. It is a reminder that everything we see, the galaxies, the stars, the atoms in your body, arose from conditions encoded in that light. The uniformity of the CMB is not just a scientific fact, it is a poetic one. It means that wherever you are in the universe, you are embraced by the same ancient glow. Whether you are on Earth or a planet in a distant galaxy, you see the same background. You are stitched into the same cosmic story, and that story begins with light that traveled for billions of years, unchanged and uninterrupted, to reach your eyes and instruments. That is why the cosmic microwave background is more than radiation. It is a message, a fingerprint, a clue. It speaks of unity, of beginnings, of the silent balance that shaped everything that followed. And perhaps most astonishing of all is that we can measure it, understand it, and reflect on it. Conscious beings, evolved from dust, listening to the first light the universe ever gave. Your position in the universe is meaningless without context. No matter how far you travel, how precise your instruments become, or how many cosmic maps you draw, asking where you are in the universe turns out to be a far more slippery question than it first appears. Not because space is too big to comprehend or our tools are not good enough, but because in the deepest sense, your position in the universe has no absolute meaning at all without context. And the more you try to pin yourself to some ultimate cosmic coordinate, the more you discover that there is no universal reference frame, no divine grid with fixed origins, no privileged spot in all of existence from which everything else is measured. Instead, location is always a relationship, always relative, always defined by what surrounds you and how those things move, in connection with you. And in a universe built on the fabric of relativity, context is not just helpful, it is everything from your everyday experience. Position seems obvious. You know where you are in your room, where your building is on your street, and where Earth is in the solar system. You can point at maps, write down coordinates, give directions. But each of these positions is defined only by what surrounds them. Your room is located inside your home, which sits on a plot of land, which is part of a city on a rotating planet, orbiting a star in a galaxy that's drifting through a local cluster. And this chain never ends. Each position only makes sense because of its connections. There is no such thing as here in the absolute. There is only here relative to there. And this realization grows more profound the deeper into physics you go. In Newton's time, people imagined space as a kind of stage, a backdrop that existed independently of the things within it. You could assign coordinates to every point in space, and motion was measured as change within this fixed arena. But with Einstein's theories of relativity, that view was dismantled. Space and time were no longer static arenas. They became dynamic, bending and stretching in response to matter and energy. There is no fixed stage behind the scenes, just the relationships between events. And, in general relativity, position itself becomes dependent on the geometry of space-time, which is influenced by the very objects you're trying to locate. If a massive object bends space, then your idea of a straight line, of a fixed point, of over there, changes. Even time flows differently depending on how close you are to mass or how fast you are moving. So, if you ask where you are, the most accurate answer might be, relative to what? Without another object or event to compare yourself to, your position is undefined. Imagine floating in a featureless void, with no stars, no planets, no light, nothing but yourself. How would you even know you were moving? How would you define direction? Without a second thing to relate to, your motion becomes meaningless. This is not philosophical poetry, it's physical truth. In such a void, velocity cannot be measured, because velocity requires change relative to something else. Even rotation becomes unknowable, because spin can only be sensed if it causes effects on surrounding objects, like the way a spinning fluid bulges outward. Without context, even that is gone. And so the universe teaches us a humbling lesson. Existence alone does not give you a position, only relationships do. This is why GPS satellites, for example, don't locate you by reading your absolute coordinates in space, but by measuring the time delays from multiple satellites, triangulating your position based on signals and distances. Your phone doesn't ask, "Where am I?" It asks, "How far am I from each of these known places?" And only then, through a network of relationships, does it construct a location. Cosmology works the same way. Astronomers don't know where Earth is in the universe by some universal address. They know we are part of the local group of galaxies, which is part of the Virgo supercluster, which lies in the Laniakea supercluster, itself moving in a certain direction relative to the cosmic microwave background. But even that background, the ancient light from the early universe, is not a fixed backdrop. It is just another field, another reference, another there to define our here. And when we measure our motion relative to it, we find we are moving at around 5 kilometers per second. But what does that really mean? It only means something because the CMB exists, because there is something to compare to. Without it, motion is undefined. This is the deep insight of relativity. There is no absolute space, no universal grid marking the universe's origin. All location, all movement, all speed, everything is relational. And this has profound implications, not just for physics, but for how we understand ourselves. It means that where you are cannot be separated from what you are near. That your place in the universe is not a number, but a relationship. You are not a dot on a map. You are a node in a web connected by invisible threads of gravity, motion, light, and information to everything else that exists. And this web is always shifting. Galaxies drift, stars orbit, planets wobble. Even you, standing still, are rotating with Earth, circling the sun, being pulled by the galaxy, drawn toward the great attractor, and possibly even being swept along by the expansion of space itself. All of these motions are real, but only relative to other things. If everything else vanished, your position would become meaningless. Even time itself would lose its rhythm, because clocks tick differently depending on speed and gravity. In this light, The very idea of center begins to fade. In a uniformly expanding universe, every point appears to be the center from its own perspective. There is no cosmic capital city, no privileged seat of existence. The Big Bang did not happen at a spot in space. It happened everywhere at once. The expansion happened not from a place, but of space. This is why galaxies see each other moving away in all directions. Not because any one galaxy is special, but because space is growing uniformly. Your place in that space is not above, below, ahead, or behind. It is simply part of the whole. And the only way to understand where you are is to understand how you relate to the rest. The stars you see are not scattered randomly. They form patterns, alignments, flows. The structure of the universe has filaments, clusters, voids. You exist on the edge of one spiral arm in a medium-sized galaxy among trillions. But even that description is not complete. It only gains meaning when compared to others. You are here because everything else is there. This relational nature of position also means that the universe resists simplification. You cannot collapse it into a single viewpoint. There is no God's eye view, no universal map that everyone agrees on. Instead, each observer has their own perspective, their own time, their own sense of now, and their own version of where things are. Two observers moving relative to each other will disagree about when events happen and where they occur, and both will be right. This is not a flaw. It is the nature of space-time. So the next time you look at a star and wonder how far it is, remember that distance is not a simple number. It depends on how you measure, when you measure, and what you compare to. Your position is not a standalone fact. It is a story, a relationship, a chapter in the book of cosmic interactions. And if that sounds complicated, it is only because the universe is richer than our instincts can handle. Yet there is beauty in that complexity. There is humility in knowing you are not fixed, not central, not absolute. And there is meaning in realizing that your position becomes real only through connection, with planets, with light, with history, with others. You are not nowhere. You are everywhere. Something else says you are, and that, in the end, may be the most profound location of all. You can't travel to the beginning. It's everywhere. Everyone has, at some point, asked where it all began, where the universe came from. What point in space gave birth to the stars, galaxies, and everything we know? But the deeper you look into that question, the more surprising the answer becomes. Because in the language of modern cosmology, there is no single place where the universe began, no specific direction you can travel to find the origin, no distant location where time and space first ignited. Instead, the beginning happened everywhere at once. All of space expanding from a hot, dense state, not from a center outward, but from every point in every direction. And this realization overturns the intuitive idea of the universe, starting from a dot in empty space and spreading out like an explosion, because the Big Bang was not an explosion in space. It was an explosion of space. And that means, if you were to rewind the universe back to its earliest moment, you wouldn't find a spot to aim for, a center to reach, or a boundary you could cross to arrive at the beginning, because wherever you are now, that is where the beginning happened too. To understand how such a strange claim can be true, you have to unlearn what your everyday experience tells you about explosions, origins, and movement. When something explodes, say, a firework or a bomb, it starts from a fixed point and sends fragments outward through pre-existing space. You can always find where the explosion occurred by tracing the paths of the flying pieces back to a center. But the Big Bang was nothing like that. There was no pre-existing space it expanded into. Space itself was created in that event, all of it. And since every point in the current universe was once compressed into that early hot state, every point shares the same claim to being the beginning. This is not just theory, it is backed by observation. When astronomers look out into deep space, they are also looking back in time. Light from distant galaxies takes billions of years to reach us, so we see them as they were long ago. And no matter which direction we look, we see galaxies moving away from us, with more distant ones receding faster, in a pattern known as Hubble's law. At first glance, this might make it seem like we are at the center of expansion. But we are not. Any observer, anywhere in the universe, would see the same thing. From their point of view, everything else would appear to be moving away. This is the key. The expansion of the universe is uniform and isotropic. It happens equally in all places and directions. There is no center, no privileged spot, no cosmic bullseye. The idea that the universe had a beginning everywhere is rooted in this symmetry. Think of the surface of an inflating balloon, not as something in three-dimensional space, but as a two-dimensional analogy. If ants were living on the surface of the balloon, they could walk around, measure distances, and observe that every point on the surface is getting farther from every other point as the balloon expands. But there would be no center of expansion on the surface itself. The center would be in a third dimension they cannot access. In our universe, space is three-dimensional, and the center of expansion, if it even exists, is not located within our observable reality. What we observe is that the universe is getting larger over time, not into something, but through the stretching of space itself. This stretching occurred uniformly everywhere. And so, the point where the Big Bang happened was not over there, it was here, and there, and everywhere else. This leads to the stunning implication that the place you are sitting in right now is as old as the cosmos itself. The atoms in your body are sitting in a piece of space that once was part of the fireball that began it all. The Big Bang didn't happen at a location in space, it happened to space, and it still is. The expansion continues even now, and that original beginning is not somewhere in the distance. It is stitched into the fabric of the present moment. You are not removed from the origin, you are immersed in it. But this idea is more than just a poetic curiosity. It has deep implications for how we understand motion, direction, and time. For instance, imagine you wanted to build a spaceship to fly to the beginning of the universe. Which direction would you go? How far would you travel? The truth is, no matter where you go, you're still inside the same fabric that began with the Big Bang. There is no edge you can reach, no external vantage point from which to view the whole thing. This is why cosmologists say the universe is homogeneous and isotropic on large scales. It looks the same everywhere, and it behaves the same in all directions. There is no center because the entire universe is the center. Every location carries the full history of cosmic evolution. When we measure the cosmic microwave background, we are not detecting a glow from some distant central fire. We are detecting the cooled-down echo of the early universe that exists all around us, in all directions, because that early fireball was all around us. You are swimming in ancient light. That background is not coming from a place. It is coming from the moment when the universe became transparent, when photons were finally free to move through space. And those photons have been moving through the same fabric ever since. Even more remarkably, this understanding shifts how we think about time. If the Big Bang was not a place but a moment, a state of the entire universe, then our search for origins becomes a study of moments, not locations. The past is not somewhere over the horizon. It is layered within the very structure of the present. The redshift we see in distant galaxies is not because they are rushing away through a void, but because the space between us and them is stretching. And that space, wherever it may be, was once hot, dense, and unimaginably small. So if you could somehow freeze time and pick any spot in the cosmos, then rewind the expansion, you would find that spot heating up, compressing, and ultimately merging into the same primordial state. This is what we mean when we say the beginning was everywhere. The early universe was not a ball of matter in empty space. It was space itself, filled with energy, expanding and cooling. That early state was uniform, not concentrated in one place. And because space itself is still expanding, we are still participating in the same event. The past is not behind us, it is beneath us. It forms the ground we walk on, and so to ask where the beginning is to miss the point. The beginning is not where, but when. And that when applies to all of space simultaneously. Every atom in the universe carries a timestamp. Every photon is a time traveler. You do not need to move to find the origin. It is part of your own history, your own position, your own surroundings. The Big Bang is not over. Its effects are still unfolding. Its expansion is still driving galaxies apart. Its ancient light is still streaming into our detectors. And its message is still etched into every particle, every fluctuation, every inch of space. So the next time someone asks where the universe began, you can smile and answer, here, right here, and everywhere else. Because the beginning was not a dot in the distance. It was the moment that created distance. The moment that space itself came into being. And because that space includes everything, the origin is not something we left behind. It is something we are still living inside. There's no universal clock. Time flows differently across the cosmos. Somewhere far away from where you are right now, in the deepest regions of a distant galaxy, or near the rim of a black hole, time is flowing, but not at the same rate it flows for you. And if this sounds like science fiction or poetic exaggeration, it is not, because in our real, measurable, physical universe, time is not a single, universal rhythm beating the same everywhere, but a flexible, dynamic phenomenon that bends and stretches depending on where you are, how fast you are moving, and what gravitational fields surround you, which means there is no master clock ticking in the background of the cosmos, no single time that governs all of existence. And instead, every object, every observer, every particle carries its own version of time, its own ticking heart, its own measure of duration, so that the question, what time is it in the universe, becomes as meaningless as asking where the edge of space is, because time in our universe is local, not global, and this realization not only rewrites our understanding of time itself, but also challenges the way we see our place within this ever-unfolding cosmic story. For most of human history, time was seen as absolute, a constant backdrop against which events occurred, like a giant clock ticking independently of the things inside it. This Newtonian view made sense in a world where everything seemed regular and predictable. Seconds, minutes, and hours ticked by the same for everyone, everywhere. But all of that changed with Einstein. In 1905, his theory of special relativity introduced the idea that time and space are linked, forming a single fabric called spacetime. And within this framework, time is not a universal constant, but something that depends entirely on your frame of reference. If two observers are moving relative to each other, they will not agree on how much time has passed between two events. A clock on a fast-moving spaceship will tick slower than one on Earth, a phenomenon known as time dilation. And it is not just a theoretical oddity. It has been measured and confirmed with astonishing precision. Astronauts on the International Space Station experience time slightly differently from people on the surface. Their clocks run just a little slower because they are moving quickly relative to Earth. But then, Einstein's general theory of relativity, published in 1915, added a deeper twist. It showed that gravity also affects the flow of time. The stronger the gravitational field, the slower time moves. This means that a clock on the surface of Earth ticks more slowly than a clock on a mountaintop, and a clock near a black hole ticks far more slowly than one floating in empty intergalactic space. This is not metaphor. It is physical reality, verified by experiments, satellites, and measurements, so accurate they influence the functioning of GPS systems. Without accounting for time dilation, due to both velocity and gravity, your smartphone's navigation would be wildly inaccurate. Time, it turns out, is elastic. It stretches and compresses depending on where and how you are. And when you zoom out to the scale of the entire universe, this elasticity becomes even more dramatic, across billions of light years, in galaxies moving away from us at incredible speeds. Due to the expansion of space, time flows at rates we can only infer from the redshift of their light. Light from a galaxy billions of years away is not only dimmer and redder because of distance, it is delayed, stretched, and altered because the rate at which time passed in that galaxy, and during its journey to us, is not the same as the rate at which time flows here. The farther back we look, the more we are peering into a different version of time, and yet, all of these times are valid. There is no correct cosmic time, no universal now. Each place, each motion, each field writes its own clock. Even the concept of simultaneity, the idea that two things can happen at the same time, is destroyed by relativity. Two observers moving differently can disagree about the order of events, and both be right. This is not a glitch in the theory, it is the nature of space-time. The deeper implication of this is staggering. It means that the universe is not a movie playing out frame by frame, synchronized across all corners of existence. Instead, it is more like a vast multidimensional fabric, where each observer threads their own path through time, weaving a unique version of history, present, and future. There is no master timeline. There is only the perspective-dependent unfolding of reality. This also raises philosophical questions about causality and destiny. If different observers have different versions of time, what does it mean for cause and effect? What happens when events that are simultaneous for one observer are not for another? Are there regions of the universe that, from our point of view, are still frozen in the past, or already in the future? The answer is yes, depending on how you move and where you are. This does not mean time travel in the science fiction sense is easy or even possible. But it does mean that our classical idea of a shared objective timeline is an illusion. Time is not a river flowing past us at a fixed speed. It is a landscape we move through, shaped by gravity, motion, and energy. And like any landscape, your experience of it depends on your path. This understanding has real, measurable consequences. In the 1970s, scientists flew extremely accurate atomic clocks on airplanes and compared them with identical clocks left on the ground. The results matched Einstein's predictions. The flying clocks had lost time. Today, GPS satellites must constantly correct their onboard clocks for both special and general relativity, or their data would drift out of sync with Earth-based receivers. In experiments with particles moving near the speed of light, unstable particles live longer than they would at rest, because time for them slows down. Even near black holes, where gravity becomes extreme, time becomes so distorted that an hour outside the black hole might correspond to years inside. This is not just a curious idea. It is something we build into the mathematics of our space missions, our physics experiments, our understanding of the cosmos. When you think of the age of the universe, around 13.8 billion years, that number is only meaningful from a specific frame of reference. In some distant part of the universe, the story may have unfolded differently. The stars there might be younger or older in their own clocks. And when you look up at the night sky, you are not seeing the present. You are seeing countless different versions of time, stitched together into a glowing mosaic of the past. Each photon that reaches your eye is a message from another clock, another history, another pace of existence. So what does it mean to live in a universe without a universal clock? It means we must abandon the idea of being synchronized with the cosmos. There is no ticking metronome governing all things. Time is deeply personal, not in the emotional sense, but in the physical one. Your body experiences time differently from someone climbing a mountain, flying in a jet, or orbiting a neutron star. Even your heartbeat is part of a localized rhythm in a universe filled with millions of others. And yet, we navigate it. We coordinate, measure, and live within these varied timelines as if they were one. Our tools are so precise that we can bridge the gaps between these flows. We define time zones, coordinate telescopes, launch missions across light years, all within a framework where time is local, not universal. This is one of humanity's greatest achievements, to live in a universe of fragmented time, yet act as if we share it. And perhaps that is the lesson in a universe without a single clock. Meaning emerges not from synchronization, but from connection, from building relationships across time's fluid edges, from realizing that every moment, for every observer, is uniquely valid, that every corner of the cosmos pulses with its own heartbeat. And in this intricate orchestra of time, no two notes are identical, yet all belong to the same unfolding song. Space might not be real, just a mental construction. When you reach out your hand, take a step forward, or gaze at the horizon, it feels so obvious that space is something real, an invisible stage stretched before your body, allowing distance to exist, giving shape to direction, volume to objects, and movement to your thoughts. But the deeper science digs, and the more precisely physics and neuroscience probe into the foundations of reality, the more one unsettling question keeps resurfacing. What if space is not actually out there in the way we think it is? Not some container that holds things, but a clever internal illusion crafted by the brain. A mental map projected outward by a system that evolved to organize sensory inputs. And what we perceive as the three-dimensional world might not be a fundamental feature of reality at all, but a constructed experience, useful, convincing, yet ultimately a story our minds tell us to make sense of something far stranger. To understand how such a radical idea can even be entertained by science, you have to pull back from the assumption that what we feel and see matches what is really there. Our ancestors evolved to survive, not to see truth. A predator's movement, the distance to a fruit, the shape of a cliff. These perceptions were honed by evolution to be useful approximations, not faithful mirrors of external reality. And when neuroscientists began examining how the brain builds spatial awareness, they discovered something astonishing. Your sense of space is not something passively received from the world, but actively created by neural processes. The visual system, the vestibular system, somatosensory feedback, and memory all combine to create the illusion of being inside a three-dimensional theater. But remove or disrupt these systems, and the perception of space can collapse or distort in dramatic ways. Stroke victims can lose half their spatial field. Some patients can feel detached from their own body. Others can no longer judge distance or size. This suggests space, at least as we experience it, is not a given. It is built, but the strangeness goes far beyond biology. In physics, especially at the quantum and cosmological levels, space stops behaving like a fixed arena and begins to unravel into something deeply counterintuitive. In Einstein's general relativity, space is not a passive backdrop. It bends and curves in response to mass and energy. Time and space are interwoven. They are not separate substances, but parts of a dynamic geometry that changes. This already challenges the notion of space being absolute. But quantum physics takes the deconstruction even further. At the smallest scales, when we examine the behavior of particles and fields, the concept of precise location becomes fuzzy. The uncertainty principle forbids us from knowing both a particle's position and momentum perfectly. Space becomes blurry, probabilistic, more like a set of relational possibilities than fixed coordinates. And in some emerging theories of quantum gravity, such as loop quantum gravity or emergent spacetime models, space is not even fundamental. It arises from more basic units of information or interaction. In these models, what we call spaces is the result of relationships between quantum events. There is no empty container. There are only links between things, and the geometry we experience emerges from the structure of those links. Space, then, is not something that exists on its own. It is something that arises when enough connections form. In string theory and the holographic principle, a similar idea appears, that our familiar three-dimensional space might be a projection from a more fundamental, two-dimensional boundary. This idea is not metaphorical, it is mathematical. Calculations of black hole entropy, quantum entanglement, and gravitational effects all support the possibility that space, as we know it, may be encoded in patterns of information rather than continuous dimensions. This view flips everything, instead of space containing information. And this brings us closer to the idea that space is not an external feature of the universe, but an emergent property of something deeper. But perhaps the most unsettling support for the unreality of space comes from an unexpected place: quantum entanglement. When two particles become entangled, their properties remain connected regardless of the distance between them. If you measure one, the other reacts instantly. This seems to defy the idea of space as a separator. In fact, some physicists now believe that space-time itself might be built from entanglement. That is, the very fabric of space is woven by quantum connections. In this view, 2 points in space feel distant only because they share little entanglement. Increase the entanglement, and the effective distance shrinks. This means that what we perceive as proximity or remoteness is not a physical fact, but a measure of information correlation. The consequences are profound. Space might be like a user interface, a way to represent complex, underlying information in a form that is navigable, just as icons on your phone screen do not reveal the true code and circuits underneath, but let you interact with them efficiently. So too might your experience of three-dimensional space be a simplified projection of an underlying computational or relational structure. We live not in space, but in a story of space. Neuroscience and physics meet in this idea. Your brain constructs a spatial model from inputs, and nature itself might be doing the same thing at a more fundamental level. The spatial experience is then a mirroring of deeper structures, not a literal observation. This reshapes our understanding of motion. If space is emergent, then movement is not something that occurs through a pre-existing void. It is a change in relationships, an update in the structure of connections, and time too becomes suspect, since it is inseparable from space in relativity. If space is constructed, time might be as well. The entire space-time stage may be a hologram generated by a process we have yet to fully grasp, and yet we navigate it intuitively. We walk, run, dream, and plan in spatial terms. That illusion, if it is one, is stable and useful, but it can break. Astronauts in orbit lose their sense of up and down. Sensory deprivation tanks erase the body's borders. Advanced virtual reality systems can fool the brain into feeling that empty air is solid ground. In dreams, space feels real, yet is entirely fabricated. All of this shows that the experience of space is remarkably easy to simulate, which begs the question: if space can be so easily faked, how confident can we be that it is fundamentally real? If you woke up tomorrow in a simulated world, indistinguishable from this one, what would give it away? If space is a perceptual construction, it may be impossible to tell. So, what are we to make of all this? Should we abandon the concept of space entirely? Not necessarily. Even if space is emergent, it remains one of the most powerful tools we have for organizing reality. Mathematics, physics, architecture, engineering, all depend on spatial models. But we must hold this concept lightly, like color or sound. Space may not exist independently of observers. It may be a feature of interaction, not of existence. And that humbling possibility challenges the deepest assumptions we carry. It asks us to reconsider what it means to be here, not in a location, but in a web of relations, not floating in a container, but embedded in a network of meaning. So when you stretch your arm, or walk through a doorway, or gaze into the night sky, remember this: the space you feel may not be a thing you move through, but a reality your mind constructs. An interface, a narrative, a geometry rising from the dance of information, not less real for being built, but more mysterious for being built so well. And perhaps the universe, in its most honest form, has no where. Only how. Not distance, but difference. Not location, but connection. And in knowing that, you are not lost in space. You are space, experiencing itself. The fabric of space-time isn't anchored to anything. Stand on the surface of the Earth, and you feel anchored, your feet pressed into the floor. The pull of gravity wrapping around you like an invisible tether, a force that gives everything direction and orientation. But step back far enough, beyond the ground and the sky, beyond the solar system and the stars, and ask yourself this: what is all of this anchored to? Really, what holds the stars in place? What fixes the galaxies? What pins the universe down so that space and time have somewhere to unfold? The answer, as strange and counterintuitive as it may sound, is that the fabric of space-time itself, the very stage upon which everything plays out, is not attached to anything at all. It floats, stretches, curves, and expands with no foundation beneath it, no external frame keeping it steady, no cosmic wall for it to lean on. It is not suspended in anything. It is the thing. And this fact is not philosophical musing. It is a cornerstone of modern physics, deeply embedded in the mathematics of general relativity, observational cosmology, and even the logic of quantum field theory. Space-time does not need to be fixed to something else to exist. It is not painted onto a canvas. It is the canvas, and like a canvas that can stretch, tear, ripple, and twist, space-time behaves not like an empty void, but like a living geometric structure that responds to energy, mass, and motion in ways that redefine what it means for something to be, where, or when. To grasp how wild this idea truly is, consider the history of how humans once imagined space. For centuries, space was thought to be a container, an infinite box within which matter existed and moved. Newton's space, in classical mechanics, was an absolute framework, a kind of invisible scaffolding that remained unmoved while planets orbited. Objects fell, and time ticked forward. It was an arena, constant and unchangeable, necessary for defining motion and acceleration. This Newtonian view implied that, even if you removed all matter, space would still be there, serene and unaffected, acting as the silent stage beneath the cosmic performance. But Einstein shattered that image with his general theory of relativity. In his vision, space and time were not separate entities, nor were they static or absolute. They were dynamic, interwoven, and malleable. Gravity was no longer a force transmitted across empty space. It was the bending of space-time itself caused by mass and energy. When Newton saw an invisible hand pulling on objects, Einstein saw a curved road that guided them. And most shockingly, this space-time was not floating on anything. It did not need a background structure. It curved and stretched and evolved based entirely on what was in it. If you removed all the matter, space-time would not reveal a hidden platform beneath. It would change. Perhaps it would become flat, or shrink, or even vanish, but it would not expose a foundation. There is none. The fabric of space-time is self-referential. It defines its own geometry. There is no absolute position, no preferred coordinate system, no ultimate anchor outside of it. All motion, all measurements, all frames of reference are internal. The laws of physics apply the same way, no matter where you are or how you're moving, as long as you account for your position and velocity relative to other things. This principle, called general covariance, is one of the deep symmetries of nature. It tells us that the equations governing space-time do not depend on an external frame. They are form, invariant. They are self-contained, and that has mind-bending implications. Imagine a vast sheet of rubber that can stretch and twist depending on what lies on it. That sheet represents space-time. Drop a bowling ball onto it, and the sheet curves. Marbles roll toward the ball, not because there is a hidden string pulling them, but because the sheet tells them how to move. Now take away the sheet. What are the marbles sitting on? What does the ball bend without the sheet? The analogy falls apart. But in reality, there is no deeper flaw beneath space-time. The rubber sheet is not resting on a table. It defines the table. It is the table, and when space-time stretches due to the expansion of the universe, it is not being pulled outward by some external pressure. It is not ballooning into a higher dimensional space. It is simply changing its own internal geometry. Space creates more of itself. Time flows differently depending on where you are. And all of this happens without being anchored. This becomes even more evident when you look at the expansion of the universe. Since the Big Bang, space has been stretching everywhere. Not from a central point, not into pre-existing emptiness, but from within itself. Every point in space, moves away from every other point. Not because they are traveling through space like objects in motion, but because space itself is expanding. And this expansion is not measured relative to an external grid. There is no outside to expand into. The universe does not need room to grow. It defines the room. The metric, the thing that tells you how far apart 2 points are, is itself changing. The ruler is stretching as you measure with it. And so, when you ask, what is the universe expanding into? Or what is space attached to? The answer is simply nothing. The question assumes an external frame that does not exist. The universe is not embedded in a larger space. Space-time is all there is, and it has no walls, no edge, no foundation beneath. It is a self-contained structure. Even black holes, those mysterious wells of curved space-time, do not tunnel into another realm. They bend the fabric around them. But there is no cosmic floor they punch through. There is no scaffold they rest upon. The singularity at their core may be a boundary in the geometry, a place where our equations break down, but it is not a hole in a wall. It is a failure of our model to describe extreme curvature, not a gateway to an outside. This lack of anchoring also raises profound questions in quantum gravity, the still, missing theory that would unite general relativity with quantum mechanics. In loop quantum gravity, space-time itself is thought to be quantized, made up of tiny loops of information, a fabric not continuous, but woven from discrete bits. In these theories, space does not even exist as a smooth stage, until these bits arrange themselves into a pattern. It emerges there is no anchor, because there is no need for one. The connections between loops define the shape. No background required. In other approaches like string theory, space-time might be a secondary consequence of vibrating strings or higher dimensional objects. Again, it emerges from something more fundamental, not something below it. In both views, space-time has no foundation because it is not the bottom. It is the layer that arises when deeper structures organize themselves. Even more radically, the holographic principle suggests that everything we experience inside a volume of space might be encoded on its boundary, just like a hologram contains three-dimensional images in a two-dimensional film. If this is true, then space and time as we know them are emergent illusions. Useful, coherent, but not rooted in anything deeper than information. In that view, asking what space-time is anchored to is like asking what the surface of a soap bubble is pinned to in the air. It is held together by tension and structure, not by attachment to anything external. This entire shift in understanding is not just theoretical. It changes how we think about existence itself. We tend to associate realness with solidity, with being tied down, with having a base. But space-time does not follow that intuition. Its freedom, its lack of anchoring, is not a weakness. It is its defining feature. It is why the universe can expand. It is why gravity bends paths. It is why no point is special. The geometry of space-time is free to evolve, unmoored from anything beyond itself. And this gives rise to the richness of cosmic structure. Galaxies form, stars burn, light travels, all within a fabric that anchors nothing, yet supports everything. So the next time you imagine the universe as something sitting in a giant room, floating in a box, expanding into a vast darkness, pause. That image is wrong. The universe is not sitting on anything. Space does not need a place to be. Time does not tick from a cosmic clock on the wall. The fabric of space-time is not held in place. It is not suspended. It is self-sustaining, self-defining, and endlessly surprising. It is the greatest stage ever built, and it builds itself without nails, without beams, without a floor beneath. And you, right now, are moving through that floating, shifting, curved, and expanding structure. Not on top of it, but within it. Not anchored by it, but part of it. And that changes everything. The center is a mental illusion, not a physical place. Look in any direction across the vast sky. Pick a spot, north, south, up, down, forward, backward, and no matter where you are in the universe, it is easy to feel as though there should be a center, some definitive middle point from which all things extend outward. A heart of the cosmos that marks the origin, the balance point, the absolute here that defines all there. But the more precisely science has measured, modeled, and observed the universe, the clearer it has become that this deeply intuitive idea of a central location is not only wrong, but impossible. And what feels like the center is not a place in space, but a mental projection, an artifact of how we perceive patterns and structure. Because in truth, the universe has no center at all. No cosmic nucleus, no privileged vantage point, no master location from which distance, motion, or meaning emanates, and the sensation of being at the center is a built-in illusion generated by the way we experience space and time from within, not an external truth about how the universe is shaped. To understand why the center is a mental construct and not a physical feature, you have to unravel some of the oldest assumptions in human thought. Since ancient times, humans placed themselves at the center of existence. In early geocentric models, Earth sat still, while the sun, moon, planets, and stars circled around it in perfect spheres. This wasn't ignorance, it was perception. The ground felt still. The stars moved across the sky. Of course, we were at the center only later, when Copernicus, Galileo, and Kepler showed that Earth was orbiting the sun and not the other way around. Did we begin to understand that being at the center was a matter of viewpoint, not truth? And even that idea had layers to peel. The sun is not the center either. It drifts in an arm of the Milky Way. And the Milky Way is not the center of the universe. It is one galaxy among hundreds of billions, each moving in its own way. So where is the center then? Where did the Big Bang happen? Where does everything expand from? The answer, strange and beautiful, is this: everywhere and nowhere. The Big Bang was not an explosion in space. It was an expansion of space itself. All of space, all at once. There was no outside to burst into. There was no edge to expand from. Every point in the universe was once compressed into that hot, dense state, and every point expanded together, which means that every point is equally valid as the origin. You are not at the center of the universe, but you are also not off-center, because the concept of a center, when applied to the universe, does not apply. This is not metaphor, this is measurement. Astronomers observe that galaxies are moving away from us in all directions, and the farther away they are, the faster they seem to recede. But this same observation would be made from any other galaxy. If you lived in a distant corner of the cosmos, you would see the same pattern, everything moving away from you. This is the hallmark of a uniformly expanding space, not a space with a single point of origin. Think again about the surface of a balloon. If you draw dots on the surface and inflate the balloon, each dot sees every other dot moving away. There is no center on the surface. The center of expansion exists in a dimension the ants crawling on the balloon cannot access. In our case, the center is not even in a higher space. It is nowhere, because the expansion of the universe is not happening from a point. It is happening to space itself. Every point of space is stretching. Every observer sees themselves as stationary, with others moving away. This creates the powerful illusion of centrality. But it is not real. It is a feature of being inside an expanding geometry. The reason this illusion persists is because human brains are wired to seek symmetry, balance, and orientation. We are creatures of perspective. We evolved to track motion, locate ourselves relative to objects, and understand position in landscapes. On Earth, every place has a center, a room, a city, a planet. We transfer this logic to the cosmos. But the universe is not a room. It has no walls, no floor, no ceiling, and no center. Even in models of the observable universe, the portion we can see based on the timelight has had to reach us. We are in the center of that sphere. But so is every other observer, wherever they are. The observable universe is not the whole universe. It is a personal bubble of sight, and the center of that bubble is you. Not because you are special, but because light reaches you from all directions equally. The illusion of being central is not evidence of being central. It is a consequence of where you stand in the structure of time and light. Take the cosmic microwave background, the afterglow of the Big Bang. It surrounds us in every direction, nearly uniform. But it does the same for anyone, anywhere. Each observer sees themselves at the center of this radiation sphere, not because there is a universal center, but because the origin of that light lies at the boundary of their observable universe. And since space is expanding, that boundary is not a wall. It is a limit imposed by the age of the universe and the speed of light. In a real physical sense, there is no anchor to pull a center from. There is only geometry, symmetry, curvature, topology. Even if the universe were finite and curved like the surface of a hypersphere, it would still have no center within it, just as there is no center on the surface of the Earth. Though it is finite, the universe can be closed and boundless, a centerless structure. And in cosmology, this is not just allowed, it is expected. The laws of physics are uniform across space. The large-scale structure of the universe, when averaged out, is homogeneous and isotropic. This means it looks the same everywhere and in every direction. There is no cosmic landmark that defines a unique origin. And so, the search for a center becomes a misunderstanding, a projection of our need for reference onto a reality that does not require it. This has deep implications for how we view not just space, but ourselves. To not be at the center is to lose a kind of existential comfort. But to realize there is no center is to gain something more profound, that you are not far from the middle, because there is no middle that your view is valid. Even if it is not privileged, that existence itself does not revolve around anything, and therefore no one is excluded from its symmetry. The center is not a physical location to travel toward. It is a mirage created by the shape of observation. And once you understand this, it transforms your view of the universe. You are not lost. You are not peripheral. You are exactly where the beginning happened, because it happened everywhere. You are exactly where light still arrives, because it arrives from all directions. You are exactly where space is expanding, because it expands in all directions. So when you look up at the sky and feel small, remember, there is no cosmic capital you are distant from, no throne of creation from which you are removed. There is no grand central point where meaning gathers. Meaning, like motion, like space, is distributed, and the center you seek is not out there. It is within, or better yet, it is a concept that never belonged to the universe in the first place. It belonged to us, and now we let it go. Not into nothingness, but into a deeper understanding that everything, everywhere, is equally part of the whole.